Heinz Ketchup, Tabasco, and Hellman's Mayonnaise are built for bold flavor with factory-level precision. From tomatoes cooked down into a glossy concentrate to peppers aged into a fiery mash, every step depends on tight timing and relentless quality checks. In this video, we follow each source from raw ingredients to sealed bottles, revealing how high-speed filling creates the products you trust every time. Tomato ketchup is manufactured as a controlled conversion of tomatoes into a stable emulsion with precise thickness, acidity, color, and pore behavior. Then it is deaerated and hot-filled, so the texture stays uniform through storage. Production starts with tomato raw material intake and primary separation. Tomatoes arrive as whole fruit for fresh processing, or as concentrated tomato paste for paste-based processing. When whole fruit is used, the first objective is to isolate edible pulp from stems and skins with minimal oxidation. Conveyors deliver tomatoes to a flume or washer where turbulence loosens soil and field debris. A dewatering screen lifts tomatoes out of the wash stream and sends them to an inspection belt that feeds a destemer and sorter. The sorter uses rollers or air jets to eject undersized pieces and hard foreign fragments. The clean tomatoes enter a crusher where rotating knives break them into a coarse mash. The mash is heated quickly to control enzyme activity that would otherwise thin the product. This is done in a hot break or cold break step, depending on the desired body. A hot break drives rapid heating to a high set point, so pectin-related enzymes are inactivated early. A cold break uses a lower heating profile that preserves fresher flavor notes but yields a thinner base. For ketchup lines that target a thick cling, a hot break-style heating is common. Heat exchangers raise temperature in seconds rather than minutes to reduce localized cooking and protect color. After heating, the mash is refined to remove skins and seeds. A pulper forces mash through perforated screens while rotating paddles sweep solids forward. A finisher follows with finer screens and higher shear to remove remaining fibrous particles. The output is tomato pulp with a controlled particle size distribution. The removed skins and seeds exit as a separate stream that is handled outside the main ketchup line. If the plant uses tomato paste as the main input, the refining step is largely upstream. Paste is received in drums or aseptic totes and stored in temperature-controlled conditions. Paste is pumped through positive displacement pumps that can handle high viscosity. Inline strainers catch gasket fragments and coagulated paste lumps. Paste is then diluted with tempered water to reach a target solids level before blending. The dilution step is staged, so water is added gradually to avoid gel lumps that resist mixing. The tomato base then enters blending and formulation. Large batch tanks or continuous blenders meter tomato base, along with sweeteners, vinegar, salt, spices, and hydrocolloids if used. Sugar may be added as granulated sugar or as liquid sweetener. Granulated sugar is dissolved in a side tank to form a syrup that blends faster and avoids graininess. Salt is added as dry crystals or as brine. Brine addition can improve dissolution speed and reduce settling in piping. Vinegar is staged in dedicated tanks with corrosion-compatible pumps and valves. Metering vinegar precisely is critical because final acidity controls flavor and stability and also changes viscosity. Vinegar is usually added after the tomato base has been warmed and mixed because cold vinegar can shock viscosity and slow blending. Some lines add part of the vinegar early for dispersion and hold the final trim addition for end-of-batch pH targeting. Spices are the most challenging stream for uniformity. Dry spices can float, then clump, then sink. Many facilities create a spice slurry using warm water or vinegar and then pump that slurry into the main blend. High shear mixers are used at the injection point, so spice particles disperse rather than forming balls. The spice slurry tank uses an agitator with wall sweep to prevent paste buildup. inline colloid mills can be placed after spice injection to reduce particle size and increase smoothness. Some ketchup formulations include a thickening system beyond tomato solids. This can involve natural gums or starches that stabilize suspension and improve cling. If starch is used, it must be hydrated and cooked to develop its viscosity. Starch is often made into a slurry first and then injected into a cooking section where temperature and shear gelatinize it. If gums are used, they are pre-blended with sugar to improve dispersion and prevent fish eyes. Gums then hydrate during controlled mixing at defined temperature and time. Once the major ingredients are combined, the mixture is heated and cooked to develop body and to integrate flavors. This cooking step can be done in steam, jacketed kettles for batch lines, or in continuous scraped surface heat exchangers for high-volume lines. Heating drives off some water and increases soluble solids. Heating also changes the tomato flavor profile by mellowing harsh notes and rounding sweetness and acidity. The line targets a specific temperature time profile that balances color retention with cooked flavor development. During cooking, the product is mixed intensely to prevent scorching. Tomato solids and sugars can stick to hot surfaces and burn if mixing is weak. Jacketed kettles use anchor agitators that scrape vessel walls. Continuous systems use scraped surface exchangers where rotating blades continuously wipe the heated surface. Scraped systems are preferred for viscous ketchup because they maintain heat transfer while limiting burn-on. Viscosity is developed through both concentration and particle interaction. Tomato cell wall fragments and soluble pectin contribute to network formation. If the process uses hot, break pulp, the network is stronger because pectin breakdown enzymes were arrested early. Solids level is monitored by inline refractometers or by periodic lab checks. Viscosity is monitored with in-process measurements and correlated to pump pressure and flow behavior. The aim is a repeatable yield stress, so ketchup holds on food, yet still flows under squeeze or tapping. After cooking, the ketchup is often homogenized or refined for texture control. Homogenization is not only for emulsions, it also reduces particle size and smooths mouthfeel. A high-pressure homogenizer forces the hot ketchup through a narrow valve, where shear breaks down aggregates. A colloid mill can perform a similar role at lower pressure by using rotor-stator shear. The chosen method depends on target texture and equipment capacity. The system is tuned so it smooths without making the product thin. Excessive shear can break the structure and reduce cling. Air management becomes important as viscosity rises. Mixing and pumping can entrain air and create foam. Entrained air causes filling errors and can dull color. It also creates microscopic bubbles that affect apparent thickness. To remove air, the line uses a deaerator. Deaeration can be done under vacuum in a vessel where ketchup flows as a thin film. Vacuum pulls dissolved gases out and collapses foam. The ketchup exits deaeration denser and glossier and more consistent in fill weight. Acidity adjustment is finalized after major processing because pH can drift with concentration and ingredient variation. Inline pH probes measure continuously, but final verification typically uses calibrated lab measurement. Vinegar trim addition can be used to hit a narrow pH target. Salt and sweetener can be trimmed as well, but acidity is the main control lever. Hitting the target pH also influences viscosity because tomato systems respond to acid levels. Color control is managed through both raw material selection and thermal exposure. Overcooking darkens ketchup and shifts hue. Insufficient cooking can leave a brighter but less integrated color. Plants monitor color with optical measurement on samples and adjust time temperature profiles. They also avoid excessive oxygen pickup because oxygen darkens tomato pigments over time. Deaeration and closed transfer help limit oxygen. Filtration and final screening protect texture and packaging. Ketchup passes through a final strainer that catches spice clumps and gasket fragments. Screen size is chosen to remove defects while keeping desired spice presence if a textured product is desired. Some lines aim for very smooth ketchup and use finer filtration. Other lines allow more particulate and rely on milling to keep it uniform. From here, the ketchup moves into the finishing tank or surge tank that feeds the filling. This tank acts as a buffer between cooking and packaging. It maintains temperature and gentle agitation. Agitation must be strong enough to prevent settling and weak enough to avoid air entrainment. Tank geometry is chosen to prevent dead zones where products can cool and thicken. Pumps feeding the filler are positive displacement pumps because ketchup is viscous and shear sensitive. Hot filling is a common packaging method. Ketchup is held at a target fill temperature that supports product stability and consistent viscosity at the moment of dosing. If filled too cool, the ketchup is thicker and may string and drip on sealing surfaces. If filled too hot, the ketchup is thinner and may lead to headspace issues and longer cooling times. Temperature is stabilized with a holding tube or a heat exchanger just upstream of the filler. The classic aged pepper sauce in the Tabasco style is produced by converting ripe chili peppers into a salted mash, fermenting that mash until acidity and aroma stabilize, separating the liquid phase, blending with vinegar to a target strength, filtering for a consistent texture, then filling under controlled temperature, so the sauce remains uniform in the bottle. Production begins with pepper selection and intake because maturity level controls capsaicin profile and the balance between bright green notes and deeper red notes. Peppers enter the facility as whole fruit and move immediately into a sorting stream that removes stems and damaged pieces. The remaining peppers are washed to remove field residues and then drained so free water does not dilute the mash. A size grading step can be used to keep downstream crushing load stable. This keeps the next machines operating at steady torque rather than surging. The cleaned peppers go to a crushing system that reduces them into a coarse pulp. The crusher uses rotating blades or a hammer-style mill depending on throughput. The goal is to rupture skins and expose interior tissue. This releases juice and allows salt to contact the cellular material. Crushing is controlled to avoid turning seeds into fine grit. Too much seed breakup raises bitterness and creates a sandy mouthfeel later. Immediately after, crushing the pepper pulp is mixed with salt. Salt addition is not a seasoning step at this point. It is a process control tool that regulates water activity and steers fermentation. Salt also pulls moisture from pepper cells, which creates a flowable mash. The salt dose is measured tightly because it sets the microbial pathway. Low salt can drive uncontrolled ferment behavior. High salt can stall fermentation and lock in harsh, raw notes. Mixing is done in a heavy-duty blender with strong folding action. The blender must distribute salt evenly through viscous pulp. Uneven salt distribution creates zones that ferment at different speeds. Those zones later produce inconsistent acidity and aroma. Mixing continues until the mash shows uniform color and consistent paste resistance. The salted mash is then moved into aging vessels. These vessels are designed for long residence time and stable temperature. The mash is packed to limit trapped air. Limited oxygen exposure helps the process move toward stable organic acid production rather than surface oxidation. Once sealed, the mash enters a slow biochemical conversion driven by naturally present microorganisms and enzymes in the pepper tissue. Fermentation converts sugars into organic acids and aromatic compounds. The main outcome is rising acidity, which preserves the mash and changes flavor from raw vegetal to rounded tangy notes. Gas generation can occur early, and the vessel design manages headspace, so pressure remains controlled. Over time, the mash becomes more uniform as cellular structure breaks down. The color deepens as pigments disperse through the paste. Temperature stability is a major lever during this aging phase. Warmer conditions accelerate conversion and can create sharper, high-acid notes. Cooler conditions slow conversion and can preserve more pepper-top notes. The facility holds temperature within a defined band to make each batch follow the same curve. Sampling systems measure acidity and solids. The target is a mature mash where acidity has leveled off and the aroma has stabilized. As aging progresses, the mash separates into phases. A liquid fraction forms as salt draws out water and as cell walls degrade. A thicker fraction remains, which contains skins and seeds and insoluble fiber. This separation is useful later because the sauce is primarily built from the liquid fraction and fine solids. The process chooses when to separate based on the desired body and heat delivery. When the mash reaches maturity, it is pumped to a separation train. The first step is a coarse screening to remove large skins and stem fragments. This uses a rotating drum screen or a vibrating sieve with a defined mesh. The screened mash then enters a press system. Belt presses or screw presses are common because they handle fibrous material well. The press squeezes the mash and releases a strong pepper brine that contains acids and dissolved solids and fine pepper particles. Press operation is adjusted to manage texture. A higher press force yields more liquid but can push fine seed fragments into the extract. A lower press force yields a cleaner extract but leaves valuable liquid in the cake. Many lines run a staged press approach. The first press yields the highest quality extract. A second press can be blended in at a controlled ratio if needed. The extracted liquid is then clarified to remove coarse grit while keeping desired pepper character. Clarification often begins with a centrifuge. The centrifuge spins the liquid and throws heavier particles outward. Solids leave as a thick concentrate and the clarified phase flows forward. Centrifuge speed and feed rate set the cut point. A tighter cut yields a cleaner sauce. A looser cut yields a more robust texture. After centrifugation, the sauce base is blended with vinegar. Vinegar serves several functions. It lifts acidity to a precise target. It adds its own volatile notes. It also helps keep insoluble pepper particles suspended by changing ionic conditions and viscosity behavior. Vinegar is metered by flow and confirmed by titratable acidity measurements. The blending tank uses controlled agitation that avoids air entrainment because foam can complicate later filtration and filling. Water may be added in some formulations to adjust strength. This is done only with controlled dosing because dilution changes heat perception. Capsaicin intensity is not only about concentration, it is also about how acid and salt change sensory delivery. The formulation is tuned so heat rises quickly on the tongue and then clears cleanly. That tuning depends on both pepper solids and acid level. The blend then enters a high shear finishing stage. The purpose is to make the sauce consistent from bottle to bottle. High shear breaks down remaining soft tissue. It reduces particle size and spreads oil droplets and pigment. Rotastator mixes are common here because they generate strong shear without high pressure. A colloid mill can also be used if the sauce needs tighter particle size control. Milling settings are chosen to avoid excessive heating, which can dull aroma. Viscosity is adjusted by controlling fine solids content rather than by adding thickening gums in a traditional minimalist style. Fine solids are managed by the earlier press and centrifuge settings. If the sauce is too thin, more fine solids are allowed into the blend. If the sauce is too thick, the clarification is tightened or the blend is diluted slightly. Consistency targets are verified using flow tests and viscosity measurements that correlate with poor behavior from the neck of a bottle. Color is stabilized through oxygen control and controlled thermal exposure. Red pepper pigments are sensitive to oxidation. Closed tanks and gentle pumps reduce oxygen pickup. Deaeration may be used after high shear mixing. Vacuum deaerators pull out dissolved air and collapse foam. This increases fill accuracy and reduces bubbles in the final bottle. It also improves color appearance by removing light scattering microbubbles. Filtration follows to protect the consumer experience and to protect packaging equipment. Filtration must balance clarity with flavor carry. A very fine filter can strip character because it removes aromatic bearing particles. A very coarse filter can allow sediment. Many lines use staged filtration. A first filter removes large remaining grit. A second filter tightens the final texture. Filter choice depends on target appearance and on how much particulate is acceptable. Hellman's mayonnaise is produced by building a stable oil in water emulsion with a controlled droplet size, then finishing texture under low air conditions, then filling so the emulsion stays glossy and thick through shelf life. Production starts with ingredient staging because mayonnaise behavior is dominated by ratios and sequence. Refined vegetable oil is stored in bulk tanks and held at a steady temperature that keeps viscosity consistent. Water is filtered and tempered because small temperature shifts change how quickly the emulsion forms. Vinegar is held in dedicated tanks and metered precisely because final acidity controls flavor and long-term stability. Egg yolk or pasteurized egg products are staged as the primary emulsifier source because lecithin and proteins anchor oil droplets. Dry ingredients are prepared as a separate stream to prevent clumping during mixing. Salt is weighed for ionic strength and taste. Sugar can be included for balance, and it is dissolved early so crystals do not remain. Mustard flour or prepared mustard is staged because it adds flavor and also contributes emulsifying and thickening behavior. If stabilizers are used, they are handled with special care because gums form lumps when added too fast. A common approach is pre-blending gums with sugar or salt so the particles disperse more evenly in water. The process builds a water phase first because the emulsion needs a continuous phase that is fully hydrated. Water enters a mixing tank and high agitation begins immediately. Salt dissolves into the water and increases conductivity and protein behavior. Sugar dissolves next and raises soluble solids slightly. Vinegar may be split into two additions, so early pH can be controlled without shocking egg proteins. Mustard and spice components are added under shear so they disperse without forming paste nodules. If hydrocolloids are part of the formula, they are introduced while the water phase is moving fast. The goal is complete hydration before oil is introduced. Hydration time matters because partially hydrated gum strands create graininess. Temperature is adjusted to a range that speeds hydration but does not denature egg proteins later. The water phase is mixed until it looks uniform and shows stable viscosity. Egg ingredients are added after the water phase is ready. Pasteurized liquid egg yolk is common because it provides consistent emulsifying strength. The egg stream is metered into the vortex so it blends instantly. The mixture becomes slightly thicker as proteins and lecithin distribute. pH is checked or inferred because egg behavior changes quickly with acidity. The tank continues mixing until the base is uniform and free of streaks. Emulsification begins when oil is introduced in a controlled ramp. Oil enters through a dosing valve that can change flow smoothly. Early oil addition is slow because the emulsion must be seeded with many small droplets. High shear heads or rotor-stator mixers create intense turbulence at the injection zone. The shear tears oil into droplets and the egg components adsorb onto each droplet surface. This adsorption prevents droplets from merging back into a larger oil pool. As the emulsion thickens, the mixing load rises sharply. The system monitors torque or motor current to track viscosity growth. Oil feed rate is adjusted to keep the mixer within its efficient range. If oil enters too fast, the emulsion can invert and become unstable. If oil enters too slow, the emulsion can overwork and become overly tight or elastic. The goal is a steady build where droplet creation matches emulsifier availability. During mid-stage emulsification, the product begins to take on the familiar mayonnaise body. Droplet crowding increases and the continuous phase becomes constrained. This produces yield stress and cling. The mixer configuration often shifts at this point. The line may move from a batch tank into an inline high shear unit. This gives more consistent droplet size because every portion passes the same shear zone. Acidity is tuned during or after oil addition depending on the target profile. Vinegar can be added late to sharpen flavor and to reach a precise pH set point. Late vinegar addition is done carefully because it can thin the emulsion temporarily. The system compensates by controlling shear and residence time, so the structure reforms. Salt can also be trimmed to match final taste and viscosity response. Once all oil is incorporated, the emulsion is refined to tighten texture. An inline homogenizer or colloid mill can reduce droplet size further. Smaller droplets increase apparent thickness and improve gloss. The refining step is balanced because excessive shear can damage the protein film on droplets. If that film is weakened, the emulsion can release oil over time. The process, therefore, targets a droplet size distribution that supports thickness without stressing the interface. Air management becomes a key focus after the main emulsion is formed. Air can be pulled in by high-speed mixing and by pump cavitation. Trapped air causes whitening and can create bubbles in jars. It also interferes with accurate filling by volume. Many lines use a vacuum deaerator where mayonnaise flows as a thin layer under vacuum. The vacuum expands bubbles and they break at the surface. The product exits denser and smoother with fewer visible voids. Temperature is controlled throughout because mayonnaise viscosity is temperature dependent. Warmer product flows more easily and reduces pump pressure. Cooler product thickens and can overload fillers. Temperature also affects droplet coalescence risk. The line aims for a stable temperature band from finishing through filling. Heat exchangers may be used to trim temperature before the filler. Before packaging, the mayonnaise passes through a final screen. This screen removes foreign particulates and any undispersed spice clumps. The screen size is chosen so it does not strip normal texture. The screened product flows into a surge tank that feeds the filler at steady pressure. The surge tank uses gentle agitation to maintain uniformity without entraining air. Filling equipment is selected for viscous emulsions. Piston fillers are common because they handle thick product with good accuracy. The piston draws mayonnaise into a cylinder and then pushes it through a nozzle. Nozzles use cut-off valves to prevent stringing. The filling motion is synchronized with container indexing to prevent smears on container rims. Containers are staged and presented to the filler in a stable pattern. Jars or squeeze bottles are oriented and spaced by star wheels or timing screws. Fill height is controlled to a target headspace. Headspace control supports consistent closure, torque behavior, and stable appearance. Some systems use a brief vacuum or gas flush at the container mouth to reduce trapped air. The goal is a clean fill surface and minimal bubble formation. Closures are applied immediately after fill. Cap application torque is controlled because it affects seal and consumer feel. For jars, the lid is pressed and then tightened to a defined torque. For squeeze bottles, the closure may include a valve cap assembly that must seat cleanly. Any product on the sealing surface can cause leaks. The line therefore aims to keep the rim clean by using accurate cut-off nozzles. After capping the containers, move through inspection and then labeling. Vision checks can confirm cap presence and confirm fill level. Weight checks can confirm dosing accuracy. Labeled units are then packed into cases. Case packing is designed to prevent excessive vibration because vibration can disturb trapped microbubbles. Finished cases are sealed and coded. The core technical success of Hellman's mayonnaise production comes from sequence control and shear control. The water phase must be fully prepared before oil addition. The oil must enter at a rate the emulsifier system can support. The shear must be strong enough to create droplets, yet not so strong that it strips protective films. The finished emulsion must be deaerated so the appearance stays smooth. The product must be filled at a stable temperature so viscosity stays consistent at the nozzle. Peanut butter production begins with the bulk intake of raw, shelled peanuts delivered in containers or silos. Peanuts are gravity-fed into hopper systems equipped with vibratory feeders that control the rate of flow into the cleaning section. Cleaning involves sequential mechanical separation units, including air classifiers, rotary drum screens, and gravity tables. Air classifiers remove lightweight debris using high-velocity airstreams. Rotary screens separate based on particle size, discarding small fragments, sticks, and foreign seeds. Gravity tables use differential vibration and airflow to isolate denser whole peanuts from lighter defective material. Cleaned peanuts are transferred via bucket elevators into temporary storage bins prior to roasting. Roasting is carried out in continuous belt roasters or rotary drum roasters depending on line capacity. Peanuts are conveyed in a single layer through a thermal tunnel with forced hot air. Drum roasters use direct heat combined with rotating tumbling action. Roasting temperature ranges from 160 degrees Cs to 180 degrees Cs, with residence times of 25 and 40 minutes. Moisture sensors at the exit point ensure target moisture reduction to below 2%. Roasting also develops flavor and reduces microbial load. Cooled air is forced across the roasted peanuts immediately upon exit. Cooling conveyors equipped with perforated belts and axial fans reduce peanut temperature to below 35 degrees Celsius to prevent oil migration or condensation. Peanuts are held in cooled hoppers with agitation to prevent bridging before entering the blanching process. Blanching removes the outer skin and splits the peanuts. This is performed in two ways: dry blanching or water blanching. Dry blanching involves friction rollers that rub off the skins as peanuts pass through serrated cylinders. Water blanching involves immersion in hot water, followed by belt conveyors fitted with rubber rollers. In both methods, skin fragments are removed by aspiration or vacuum collection systems. Split peanuts pass through inspection belts or optical sorters to remove discolored, moldy, or damaged halves. High-speed cameras scan each peanut and trigger air jets to divert off-spec material. Sorted peanuts are collected in surge hoppers and metered into grinders. Peanut grinding is performed in two stages: primary size reduction and emulsification. The first stage uses a hammer mill or disc attrition mill. Peanuts are fed into a chamber with rotating blades or abrasive plates. The initial grind reduces particle size to around 300-500 microns. The paste is then pumped into a second stage colloid mill. The colloid mill performs high shear homogenization between a rotor and stator, reducing particle size to below 100 microns. Rotor speeds exceed 3000 RPM, and the grinding gap is adjustable for texture control. The grinding process also generates frictional heat, raising product temperature to 60-80 degrees Celsius, which reduces viscosity and facilitates emulsification. During the second stage grinding, or immediately afterward, stabilizing agents and additives are introduced. Common stabilizers include fully hydrogenated vegetable oils, such as rapeseed or cottonseed oil. These are pre-melted in jacketed tanks and dosed using heated transfer pumps. Stabilizer addition typically ranges from 1 to 2% by weight and is controlled with flow meters. For sweetened or flavored varieties, additional ingredients such as sugar, salt, molasses, or cocoa powder are added through powder feeders or liquid dosing pumps. These materials are pre-weighed and incorporated in line using dynamic mixers with static mixing elements or turbine blades to ensure rapid dispersion into the viscous peanut paste. After additive incorporation, the peanut butter undergoes a degassing phase. The hot paste is transferred to a vacuum chamber or degassing tank where air bubbles are removed. The system applies vacuum pressure between 0.7 and 0.9 bar while slowly agitating the product to avoid entrapping more air. This step improves texture and packaging stability. Degassed product flows into surge tanks equipped with slow-speed agitators and thermal jackets to maintain fluidity. Temperature is held between 55 to 65 degrees AS to facilitate downstream handling. Product is then directed toward the packaging line via sanitary lobe pumps, which provide high volume transfer without shear. Before filling, the peanut butter may be passed through a scraped surface heat exchanger to adjust temperature precisely. The system uses rotating scraper blades inside a jacketed tube to maintain heat transfer efficiency without fouling. Outlet temperature is held constant, typically 50-55 degrees Celsius, for optimal flow into containers. Packaging is performed on high-speed, servo-driven filling lines. Empty jars made of PAT or PP plastic are depalletized and placed onto the conveyor. Each jar passes through an ionized air rinser that removes particulate matter. Clean jars are indexed into a rotary filler with multi-nozzle heads. Volumetric piston fillers or mass flow filling systems dispense precise quantities of peanut butter into each jar. Fill levels are controlled within plus 0.5% tolerance. Nozzles are heated or jacketed to prevent clogging due to cooling product. Some systems use bottom-up filling to prevent air entrapment and surface voids. After filling, jars proceed to the capping station. Caps are sorted and aligned using centrifugal feeders or vibratory bowls, then applied and torqued by rotary chuck cappers. Torque sensors monitor seal integrity, and improperly sealed jars are rejected automatically. If induction sealing is required, a foil liner is placed inside the cap. After capping, jars pass under an induction sealer where a high-frequency electromagnetic field heats the foil, bonding it to the jar rim. The seal creates a hermetic barrier that prevents oxygen ingress and oil separation. Labeled jars move to a wraparound or pressure-sensitive labeling station. Labels are applied using servo-controlled applicators, and optical sensors verify alignment and barcode presence. Rejected units are diverted to inspection lanes. Coded printing systems, typically thermal inkjet or laser, apply batch numbers and date codes to the lid or shoulder of each jar. The print system is synchronized with the conveyor speed to ensure clear, consistent marking. Jars are grouped into sets using collation conveyors and loaded into corrugated cartons or shrink-wrap trays. Case packers use robotic arms or mechanical pushers. Sealed cases are labeled with logistic codes and moved to palletizers. Palletizing systems stack cases using programmed layer patterns. Slip sheets are added as needed, and completed pallets are stretch-wrapped with plastic film to stabilize the load for transport. Each pallet receives an RFID tag or barcode label for warehouse tracking. Throughout production, inline sensors monitor critical parameters. These include product temperature, flow rate, fill weight, torque, seal integrity, and label placement. Data is logged by the Central Manufacturing Execution System and linked to batch tracking systems for traceability. Process water used in cleaning and ingredient dissolution is stored separately and heated as needed. All process equipment is connected to CIP systems that circulate detergent and rinse solutions through pipes, tanks, pumps, and valves at scheduled intervals. Cleaning sequences are validated using conductivity, temperature, and flow sensors. Environmental conditions such as air, temperature, humidity, and particulate levels are regulated in processing areas using HVAC systems with HEPA filtration. Maintaining a controlled environment prevents moisture pickup by roasted peanuts and ensures consistent flow behavior of the peanut paste during grinding and filling. Roasting profiles are monitored using thermal sensors and data loggers. Temperature curves are logged and compared against reference curves to ensure even development across peanut batches. Real-time moisture analyzers positioned at the roaster exit verify dehydration targets. Particle size of the final peanut butter is measured using laser diffraction or sieving techniques. Target particle size is typically below 30 microns for smooth varieties and above 100 microns for crunchy variants. Crunchy peanut butter includes the addition of roasted peanut granules, which are prepared separately using coarse grinders, and added post-homogenization under low shear to maintain particle integrity. Oil. Separation resistance is measured during quality control using centrifuge testing or accelerated shelf life studies. Stabilizer effectiveness is confirmed through oil migration testing at elevated temperatures over time. Nutella production begins with the individual preparation of its components: hazelnuts, sugar, cocoa powder, vegetable oil, skimmed milk powder, lecithin, and vanillin. Each raw material is handled separately in dedicated systems to ensure proper particle size, mixing compatibility, and thermal behavior before integration. Hazelnuts are received shelled and pre-cleaned. They are conveyed through pneumatic lines into vibratory feeders that regulate flow into pre-roasting storage silos. From these silos, hazelnuts are metered into a continuous roasting system. Roasting occurs in horizontal convection tunnels or rotating cylindrical chambers, typically at 140 degrees 160 degrees C for 20-25 minutes, depending on kernel moisture. The goal is to reach a final moisture level below 2% and to initiate flavor development. Post-roasting, nuts are directed into cooling drums or belt coolers. Forced ambient air lowers kernel temperature to below 30 degrees Celsius before further handling. The next step is blanching, where the brown skin is removed. This is done using mechanical friction rollers or pressurized steam exposure, depending on the desired throughput. Skin is separated by aspiration. The blanched nuts are then split and sorted by size via oscillating sieves, and undersized fragments are diverted. Cleaned, roasted hazelnuts are passed through a primary grinding phase using disc mills or pin mills to produce a coarse meal. This intermediate product is directed into a secondary grinding stage, often a ball mill or high-speed impact mill, which reduces particle size to a fine paste. Typical particle sizes are reduced to under 30 microns at this stage, producing a flowable hazelnut slurry with partial oil release. In parallel, sugar is handled separately. Granulated sugar is milled using air-classifying impact mills to reduce particle size and ensure dissolution in the final product. The resulting fine sugar powder is transferred pneumatically to dosing silos. A similar dry handling system is used for skimmed milk powder, which is fed into mixers via enclosed screw conveyors. Cocoa powder is stored in low humidity silos and transferred through sealed auger systems to prevent moisture absorption. It is typically defatted and pre-sifted to avoid clumps or oversized particles. All powdered ingredients, sugar, milk, and cocoa, are dry blended using horizontal ribbon blenders. These blenders operate at low speed to achieve uniform mixing without generating excess dust. The vegetable oil, primarily refined palm oil, is kept in liquid state in temperature-controlled storage tanks maintained at 45 to 50 degrees C. Oil is pumped through inline filters and metered into mixing systems via flow control valves. The oil acts as the continuous phase 4. The final emulsion and must be dosed with high consistency. All components are transferred into a batch mixing system, a stainless steel planetary mixer, or a high viscosity processing vessel equipped with anchor agitators. The sequence starts with oil and hazelnut paste, followed by gradual incorporation of the powdered mix. Agitation is applied in stages, with high torque, low speed mixing used for initial wetting and medium speed agitation for full dispersion. Lecithin, added to control emulsion stability and flow, is stored in small heated tanks and introduced last. It is pre-mixed with a portion of the oil phase and dosed via peristaltic or gear pumps. Concentration is typically around 0.3% of the total mass. Vanillin, in synthetic form or as part of a flavoring premix, is injected at low concentrations and blended briefly under vacuum to prevent volatilization. The batch undergoes a refining stage using a 5-roll or 3-roll mill. The paste is pressed through steel rollers, reducing particle agglomerates and improving surface smoothness. The rollers operate at progressively higher speeds to create shear differentials, compressing solids and distributing fat evenly. Target final particle size is below 25 microns. After refining, the product is transferred to a conche, a jacketed horizontal mixer equipped with large mixing blades. The conching phase continues kneading at elevated temperatures of 50-60 degrees Celsius for 1 to 3 hours. This step enhances mouthfeel, disperses volatile compounds, and improves gloss by coating all particles with fat. Upon completion, the paste moves to a vacuum degassing tank where trapped air is removed. Vacuum is applied at 0.8 to 0.9 bar, while slow paddles maintain circulation. This step prevents air pockets in packaging and reduces oxidative degradation. The degassed product is homogenized through a low shear inline mixer to stabilize viscosity. The finished spread is transferred via jacketed pipelines to holding tanks prior to filling. These tanks are fitted with variable speed agitators and are temperature controlled at 40-45 degrees Celsius. A load cell system measures tank contents, coordinating flow to the packaging line. Transfer is performed with sanitary-grade rotary load pumps for accurate low shear movement of viscous material. In the filling area, jars are supplied via unscramblers and aligned onto conveyors. They pass under vision cameras to confirm shape and cleanliness. Filling is done using servo-controlled piston fillers or mass flow metering systems. Fill nozzles are jacketed and temperature controlled to maintain flow characteristics. Fill volumes are typically accurate to within plus 0.5%. After filling, jars are sealed with aluminum foil using induction sealing. A liner is embedded inside each cap. When the cap is torqued onto the jar and passed under the induction head, an electromagnetic field heats the foil, bonding it to the jar rim. This creates an oxygen barrier and prevents oil migration. Caps are applied using rotary or inline capping machines with torque monitoring. If torque deviates from preset values, jars are rejected. Sealed jars move to the labeling station, where pressure-sensitive or shrink-wrap labels are applied. Labeling heads are adjusted for jar geometry and verified by optical sensors. Next, jars are passed under thermal inkjet printers, which apply date codes and batch identifiers. Printers are aligned with conveyor timing to ensure sharp, legible printing. Codes are verified by barcode readers or OCR systems. Rejected jars are diverted using pneumatic pushers. Labeled jars are grouped into sets using automated collation conveyors. Depending on destination, they may be packed into cardboard cartons or shrink-wrapped into trays. Cartoning machines erect boxes, load jars, and apply closure glue automatically. Case packers then arrange cartons into shipping cases with robotic arms. Shipping cases are sealed using hot melt glue applicators or tape dispensers and labeled with printed logistics data. The labeled cases are scanned, weighed, and conveyed to a palletizing station. Robotic palletizers Stack cases according to optimized patterns, using vacuum or mechanical end effectors. Pallets are wrapped using rotary arm stretch wrappers. Film is tensioned to maintain structural integrity without distorting the cartons. Pallets are tagged with scannable barcodes or RFID labels for traceability. Throughout the entire production process, all operations are controlled and logged by a PLC-driven SCADA system. This includes ingredient dosing, thermal profiles, particle size measurements, fill volumes, torque levels, and packaging throughput. Parameters are displayed on HMI terminals and stored in batch records for traceability. Strawberry jam manufacturing begins with bulk delivery of strawberries in refrigerated containers. The fruit arrives pre-sorted or in raw form depending on source. Upon unloading, strawberries are tipped into stainless steel flume tanks where they are submerged in chilled water to reduce field heat and initiate washing. The strawberries are conveyed out of the wash tank using cleated food-grade belt elevators. A high-pressure spray bar located at the discharge point removes surface contaminants. Excess water is removed by air knives or centrifugal dewatering systems. Cleaned fruit is conveyed to the inspection station. At the inspection stage, strawberries pass over a slow-moving belt or roller table equipped with manual or optical sorters. Defective, underripe, or foreign objects are removed. High-resolution cameras with multispectral imaging may be used for automatic defect detection. Rejected items are separated using pneumatic actuators or diverters. Clean, sorted strawberries are directed to the hulling station. Hulling machines use rotating rubber fingers or mechanical plungers to remove the calyx and stem. The removed portions are separated by air aspiration. Hulled fruit is transferred to a temporary buffer hopper before size reduction. The hulling hopper meters strawberries into a dicing or pulping system. Dicing machines use oscillating blades to produce uniform fruit pieces. For homogeneous jam, fruit is passed through a finisher or pulper equipped with perforated screens and rotating paddles to produce a consistent puree. Screen aperture determines the level of texture in the final product. Pulpy fruit mass is weighed using inline load cells or flow meters and directed to a batching tank. In parallel, sugar is conveyed from silos or bulk bags into a dry blending unit. Sugar is sometimes preheated or dissolved in deionized water to create a syrup. This is controlled by mass flow regulation and prepared in jacketed mixing tanks equipped with agitators. Pectin is added either as a powder or as a pre-dispersed liquid. Powdered pectin is mixed with a portion of sugar to prevent clumping during hydration. The blend is fed into the batching tank via screw feeders or high shear dispersers. The type and concentration of pectin depend on the desired gel strength and fruit acidity. Citric acid is introduced to adjust pH, typically to the range of 3.1-3.4, which optimizes pectin gelation. Acid is dosed from a separate tank using peristaltic pumps monitored by inline pH probes. The exact amount is calculated based on the natural acidity of the strawberry pulp, which is measured per batch. In certain formulations, calcium salts may be added to activate low methoxyl pectins. These are metered in precise amounts using microdosing pumps. Water content is balanced by calculating the moisture level of incoming fruit and adjusting with deionized water or fruit juice concentrates. The full formulation, strawberry mass, sugar, pectin, acid, and optional additives, is transferred to a batch vacuum cooker. The cooking vessel is a steam-jacketed stainless steel kettle, often equipped with an anchor agitator and a central high-shear rotor for uniform heat transfer and reduced localized scorching. Cooking parameters are set to evaporate excess moisture, invert part of the sucrose, and activate pectin. The process is performed under partial vacuum to allow boiling at lower temperatures, preserving color and flavor while reducing thermal degradation. Typical target solids content for jam is 65-68 degree Brix, measured with inline refractometers. During cooking, water vapor is extracted through a condenser system connected to the vacuum circuit. Condensate is collected and removed via gravity drains or vacuum traps. The jam mass is circulated continuously through the cooker using sanitary centrifugal pumps. This ensures uniform heating and prevents sedimentation of fruit particles. Once the desired bricks and viscosity are achieved, the batch is cooled through a scraped surface heat exchanger. This unit has a rotor with fixed blades that continuously remove product from the heat transfer surface, enabling rapid cooling while weighing, preventing fouling. Product temperature is reduced to below 85 degrees Celsius to prepare for filling. Deaeration is performed inline or in a separate vacuum tank. This step removes entrained air bubbles introduced during cooking and agitation. Vacuum is maintained at approximately 0.8 bar, while slow agitation is applied to stabilize the product's density and texture. Optional flavoring agents or color corrections are added at this stage. Natural strawberry flavors or concentrated fruit essences are introduced through metering systems. Any added color is dispersed into a small portion of jam and blended thoroughly to prevent streaking. The final mixture is homogenized using low shear mixers to avoid foam generation. Finished jam is held in surge tanks equipped with level sensors, slow speed agitators, and thermal jackets to maintain flowability. Surge tanks are connected to the filling system via positive displacement pumps or rotary lobe pumps that handle viscous products with suspended solids. Glass jars or plastic containers are depalletized and transferred to the filling line using timing screws and indexing star wheels. Containers are first rinsed with filtered air or ionized air jets. Jars are checked by vision systems for cleanliness and structural integrity. Jam is filled hot, usually between 80-85 degrees Celsius, to enable vacuum sealing after capping. Filling is performed using piston fillers or mass flow-based servo systems. Fill volume is precisely controlled to match container dimensions and headspace requirements. Foaming is minimized by diving nozzles that dispense product near the base of the container. Immediately after filling, containers pass through a capping station. Metal twist-off caps with vacuum buttons or plastic snap-on lids are applied by mechanical torque heads. For metal closures, steam injection may be used just before capping to displace air and create a vacuum as the container cools. Capped jars move through an inverted holding tunnel or a rotary cooling system. Cooling is carried out using ambient air or chilled water sprays to bring the product below 40 degrees Celsius. Gradual cooling prevents thermal shock to containers and promotes vacuum formation in sealed jars. Vacuum level is verified through cap button testing. Non-vacuum jars are automatically rejected. Labeling follows cooling. Jars are dried using air knives or infrared heaters before entering the labeler. Labels are applied using pressure-sensitive or hot melt glue systems, depending on the label substrate and application speed. Coded information such as production date, expiration, and batch number is printed using thermal inkjet or laser coders. Print location and clarity are verified by high-speed vision systems. Jars failing print quality checks are removed from the line. Labeled jars are grouped into cartons using robotic pick-and-place arms or mechanical collators. Cartons are formed from flat blanks, glued, and sealed using flap folders and glue guns. Carton integrity is checked by sensors measuring weight and dimensions. Cases are packed into shipping boxes or trays. Box formers erect corrugated cases, which are filled and sealed on a continuous motion line. Finished cases are conveyed to an automated palletizer, which stacks them in configured patterns for optimal stability. Pallets are conveyed to a stretch wrapping system where film is applied under tension. Each pallet is labeled with a scannable ID, linked to batch and traceability data. Wrapped pallets are moved to staging zones for distribution or temperature-controlled storage. Throughout the process, control systems monitor and log all variables. Programmable logic controllers manage dosing, cooking, filling, and packaging operations. Sensors measure temperature, flow, pressure, and viscosity. Human-machine interfaces provide operators with real-time control and alarms. Brix levels are verified at multiple points using digital inline refractometers. pH is measured with inline glass electrode probes. Final jam consistency is evaluated using rotational viscometers or Bostwick consistometers. Water activity meters confirm product stability. Nutella biscuits manufacturing begins with production of the biscuit shell using a rotary molding and baking process. The biscuit dough is prepared by blending wheat flour with vegetable fats and powdered sugar inside a continuous horizontal mixer. The mixer operates at fixed low speed to prevent gluten development while ensuring even dispersion of fat particles across the flour. Water is added near the end of the cycle to activate binding. The dough is mixed until it reaches a defined plasticity suitable for molding and is then discharged into a feeding hopper connected to the forming line. The rotary molder presses the dough into engraved cavities on a rotating drum. The cavities have an open bottom design to release formed biscuits onto a steel mesh conveyor belt. The upper roller applies pressure to ensure full cavity fill, while the scraper removes excess dough and reintroduces it into the system. Each molded shell includes a circular depression designed to receive the Nutella filling after baking. The unbaked shells are spaced at regular intervals on the conveyor to allow for controlled baking conditions. The biscuit shells are conveyed into a multi-zone tunnel oven for baking. The tunnel consists of top and bottom heating elements, independently controlled in each zone. The oven temperature rises gradually from 160 to 210 degrees Celsius across the length of the tunnel. The baking profile is optimized to achieve full moisture removal from the dough without causing expansion or deformation of the molded cavity. Residence time in the oven is calibrated to match dough moisture content and thickness. Shells exit the oven fully baked with crisp structure and low residual humidity. After baking, the biscuit shells are cooled using ambient air directed across multiple conveyors arranged in a serpentine path to reduce surface and internal temperatures evenly. Cooling is required to stabilize the biscuit structure and prepare the cavity for Nutella filling. The biscuits are held at rest until their surface temperature falls below 30 degrees Celsius to prevent filling separation. In parallel, the Nutella filling is prepared in a high-shear emulsification unit. Using sugar, skimmed milk powder, cocoa, hazelnut paste, and vegetable oils. The ingredients are pre-mixed in separate feeders and metered into a blending vessel. The vessel operates under vacuum to remove entrapped air and maintain smooth consistency. The filling is processed at controlled temperature of 40 to 45 degrees Celsius to keep the viscosity within a defined range suitable for extrusion. Once homogenized, the filling is pumped to a filling head fitted with multiple nozzles. The cooled biscuit shells are conveyed under the filling head where each cavity is aligned with a single nozzle. A volumetric piston system injects the Nutella filling into each cavity with precise volume control. The fill level is calibrated to rise just below the edge of the biscuit wall to allow sealing with the top biscuit layer. After filling, the open surface is inspected for overflow or inconsistency using machine vision systems that communicate with rejection gates for off-spec product. A second biscuit layer is prepared using a similar dough mixing and molding process, but with a flat profile and no cavity. These flat biscuits are baked and cooled on a parallel line. After cooling, they are conveyed to the sandwiching station, where they are aligned and placed on top of the filled biscuit shells. Robotic arms or mechanical pushers perform the alignment and placement. Each top biscuit is pressed gently to create full contact with the Nutella surface, ensuring mechanical bonding through surface tension of the fat-based filling. The sandwich biscuits enter a brief setting tunnel where cool air is applied to solidify the outer edges of the filling. This step reduces movement during handling and packaging. The biscuits exit the tunnel with the Nutella core enclosed between two baked shells. Completed Nutella biscuits are conveyed to a wrapping line. Each biscuit is separated by timing belts and transferred to a horizontal flow wrapping machine. Printed film is pulled from a roll and formed into a tube by a forming collar. The biscuit enters the tube, and the machine applies a longitudinal heat seal using rotating pressure rollers. End seals are created using heated sealing jaws that cut and close the wrapper simultaneously. Wrapped units are transferred to a grouping station where multiple biscuits are oriented into lanes and grouped for final packaging. Mechanical pushers move the groups into pre-formed trays or cartons, which are closed and sealed using hot melt glue. Cartons are held under compression for a fixed time to ensure glue adhesion before being moved to the final packing area. Each element of the Nutella biscuit structure is formed in distinct production zones that operate in parallel and converge during assembly. The biscuit shell relies on controlled dough plasticity, consistent cavity shaping, and uniform baking to maintain its geometry. The filling requires stable emulsification and thermal regulation to maintain deposition quality and shelf stability. Assembly depends on mechanical alignment, volumetric precision, and sealing reliability. Material flow through the plant is linear with dedicated conveyance systems connecting each station. Biscuit shells and tops are kept on separate synchronized lines to ensure timing consistency during sandwiching. The filling pump rate and nozzle actuation are matched to biscuit speed to maintain throughput. Each station includes real-time sensors to monitor dough consistency, bake color, biscuit thickness, fill weight, and seal integrity. These sensors feed data to a central programmable logic controller that adjusts line speed, pump rate, and heating elements based on tolerances. The manufacturing of Nutella biscuits depends entirely on coordinated dosing, shaping, heating, cooling, filling, sealing, and wrapping processes. Every stage transforms the materials physically by temperature or mechanical force, without the use of molding or batch processing beyond the initial dough and filling prep. All thermal zones are closed-loop systems with adjustable airflow and temperature feedback. Air velocity, humidity, and direction are optimized to control baking profiles and cooling rates. These variables determine final texture and filling retention. Filling viscosity is adjusted by temperature control and shear rate. The shear thinning nature of the filling allows fast deposition while maintaining form when static. Deposit shape is retained until enclosed by the top biscuit and set during the cooling phase. Final product dimensions are defined by the cavity shape of the rotary mold and the flatness of the sealing biscuit. Mechanical indexing ensures positional accuracy for every fill and seal. No lateral shift is tolerated at the sealing station. The top biscuit must be seated with uniform pressure to prevent leakage or deformation. This step is controlled by pneumatic actuators that apply force within a calibrated range to prevent structural damage to the shell. The flat biscuit must align concentrically with the base. All scrap or off-spec products are diverted to return belts for reprocessing or rejection. These include unfilled shells, misaligned sandwiches, overfilled units, and wrapping errors. Each rejection path is physically separated to maintain uninterrupted flow of conforming units. Finished wrapped units pass a final weight check and metal detection station before secondary packaging. Cartons are printed, coded, sealed, and stacked for dispatch. No rework is conducted beyond primary quality rejection zones. Oreo production starts with the preparation of the chocolate biscuit dough using a high-capacity continuous mixer. Dry ingredients including soft wheat, flour, sugar, cocoa powder, and leavening agents are first weighed and fed into the mixing chamber. A separate line introduces palm oil, or shortening, which is preheated to maintain fluidity and evenly distributed across the dry blend. Water is added gradually to initiate dough formation while mixing paddles rotate at low speed to prevent overdevelopment of gluten. The process continues until the dough reaches uniform consistency with defined plasticity suited for rotary molding. The mixed dough is conveyed to the forming system via an auger feed mechanism. The dough enters the hopper of a rotary molder, equipped with engraved rollers that define the embossed biscuit design. As the dough passes through the rollers, it is pressed into the cavities with precise pressure and then released onto a wire mesh baking band by means of a stripping knife. Excess dough is scraped from the roller surface and returned to the feed hopper for reuse. Biscuits are formed in continuous rows and spaced evenly to allow thermal exposure during baking. The molded biscuit pieces are carried into a multi-zone tunnel oven. The baking process is divided into sequential zones where temperature and air velocity are independently controlled. The oven begins at a moderate heat to set biscuit shape and rises to higher temperatures to complete internal baking and develop surface color. The typical baking curve ranges from 160 to 220 degrees Celsius. Each biscuit remains in the oven for 6 to 9 minutes, depending on thickness and moisture content. The mesh band allows uniform exposure to heated air on all sides. After baking, the biscuits are discharged onto a cooling conveyor where ambient air is directed from above and below to bring the temperature down gradually. The biscuits move across multiple levels or loops of conveyors to extend cooling time without occupying additional floor space. Final biscuit temperature is reduced to below 30 degrees Celsius to ensure structural stability before sandwiching. Simultaneously, the creme filling is prepared in a separate emulsification line. The filling consists of icing sugar, hydrogenated vegetable oil, soy lecithin, and flavoring agents. Ingredients are loaded into a planetary mixer equipped with high-speed blades and jacketed walls. The sugar is ground and combined with oil under shear to produce a smooth, homogeneous, fat-based paste. Temperature is maintained between 35 and 40 degrees Celsius to control viscosity and ensure pumpability. Once mixed, the filling is transferred to a holding tank fitted with agitators to prevent settling or phase separation. The cooled biscuits are conveyed into the sandwiching station in a synchronized line. They are separated into top and bottom rows using mechanical diverters. The bottom biscuits move directly under the filling depositor, while the top biscuits follow a delayed path to allow time for the filling application. The depositor contains multiple nozzles aligned with each lane of biscuits. Each nozzle dispenses a fixed volume of cream using a positive displacement piston pump. The deposit is placed at the center of each biscuit with consistent diameter and height. Top biscuits are aligned and placed onto the filled base biscuits by a pick and place mechanism. A servo-controlled arm picks the top halves and lowers them precisely onto the creme layer. The contact pressure is adjusted to spread the filling evenly without causing overflow. The result is a sandwich structure with a defined creme layer held between two embossed chocolate biscuits. Each finished sandwich is inspected for alignment and fill consistency using vision sensors and rejected automatically if outside tolerance. Sandwiched Oreos are then conveyed to the packaging section. The product flow is timed to match the entry speed of the horizontal flow wrapping machine. Wrapping film is unrolled and passed through a former to create a continuous tube. The Oreos enter the tube and are enclosed longitudinally using heated crimp rollers. Transverse end seals are applied using rotating sealing jaws that cut and seal each package simultaneously. Seal parameters are adjusted for film thickness and product temperature. The wrapped Oreos exit the machine in a sealed pillow pack configuration. Multiple wrapped packs are grouped into secondary packaging units using collection conveyors and counting gates. Depending on the product format, they may be stacked or aligned edge to edge, and loaded into pre-formed cartons. Cartons are formed from flat blanks using folding arms and sealed with hot melt glue. Filled cartons are compressed briefly to ensure adhesive bond and discharged onto the final conveyor. Each line operates continuously and is monitored by sensors that track biscuit position, deposit weight, package seal integrity, and material usage. The entire process is controlled by a centralized PLC system that coordinates line speed, temperature settings, pump pressures, and mechanical alignment across all stages. Biscuit texture is determined by dough moisture content, oven temperature profile, and baking time. Creme consistency is controlled through oil phase properties, shear rate, and deposition temperature. Assembly quality is a function of alignment precision, deposit accuracy, and pressure applied during sandwiching. Packaging integrity depends on film properties, sealing jaw temperature, and dwell time. Throughout Oreo production, no stage is batch-based beyond initial mixing. Dough and creme preparation feed into continuous mechanical systems that deposit, shape, bake, cool, fill, and wrap in a single linear sequence. Ingredient transformation is physical through heating, mixing, and compression. Structural integrity is achieved by thermal setting in the oven and mechanical bonding during sandwiching. The shape and weight of each Oreo are determined by the engraved mold cavities and the metered deposit volume. The embossed pattern is preserved by controlled dough texture and low expansion during baking. Biscuit brittleness is managed by adjusting water content and baking duration. Fill height is maintained by calibrating piston stroke length and pump cycle frequency. Every motion in the line contributes to dimensional uniformity and output consistency. Dough movement is regulated by roller speed and auger feed rate. Biscuit placement is defined by indexing and lane spacing. Creme application depends on nozzle diameter and internal deposit pressure. Sandwich closure requires precise Z-axis movement and timed application force. The rotary molding drum is cleaned automatically using scraper blades and air jets between production runs. Dough formulation is adjusted in real time based on humidity and flour batch variation. Viscosity of the creme filling is monitored using inline viscometers that signal temperature adjustments in the holding tank jacket. Oven parameters are logged continuously and used to regulate the baking curve. The production of Oreo cookies involves multiple heat and shear-based unit operations that alter physical properties without any fermentation or leavening beyond minor chemical agents. All dimensions are mechanically imposed and retained by careful control of thermal transitions and compression events. No rework is introduced into the sandwiching process. Only biscuits that meet shape, color, and thickness criteria are accepted. Filling rejects are filtered back into the holding tank through a return line. Packaging errors are removed before sealing to prevent final product contamination. The system is designed to maintain flow and reject outliers without stopping. The final Oreo structure consists of 2 rigid outer shells and 1 malleable creme layer. The shells resist deformation under handling. The creme adheres without fluid migration. Moisture barrier properties are maintained by the biscuit's low water activity and the hydrophobic nature of the fat-based filling. Nutter butter cookie production begins with the preparation of the peanut-flavored dough. Dry base materials are loaded into a large capacity horizontal mixer through automated dosing systems. These materials include soft wheat flour, granulated sugar, dextrose, baking soda, salt, and peanut flour. Separately, hydrogenated vegetable oil and peanut butter are preheated in jacketed holding tanks to reach a flowable state. The fats are pumped into the mixer and distributed over the dry mix while the paddles rotate at low speed. Water is then injected into the chamber through spray nozzles to activate hydration without overdeveloping gluten. Dough temperature is maintained between 18 and 22 degrees Celsius. The dough is mixed until a target plasticity is achieved, ensuring it can be molded without sticking or tearing. Once complete, the dough exits the mixer via a discharge chute and is conveyed to a dough feed hopper mounted above a rotary molder. The molder is equipped with engraved rollers featuring the signature peanut shell pattern and split mold design that will define the top and bottom cookie pieces of the Nutter Butter sandwich. As the dough is fed into the rotary molder, the engraved drum compresses and shapes the dough into uniform cookie halves. A fixed scraper blade removes excess dough from the roller's surface, while a vacuum-assisted mechanism ensures accurate demolding from the cavities. Formed cookies are transferred onto a wire mesh conveyor belt that transports them through a continuous tunnel oven. Excess dough is rerouted via a return auger and refed into the forming system. The tunnel oven is divided into sequential thermal zones with independent temperature control. The initial zone sets the cookie shape at approximately 160 degrees Celsius. The intermediate zones raise temperature to 200 degrees Celsius to drive off internal moisture. The final zone applies finishing heat at 220 degrees Celsius to develop the surface texture and light browning. Airflow direction and volume are adjusted separately for top and bottom heating across all zones. The wire mesh belt permits full convection exposure around each cookie piece. Total baking time ranges from 6 to 9 minutes depending on dough moisture, product thickness, and belt speed. During baking, moisture content is reduced from around 18% to below 2%. The cookies exit the oven fully formed and structurally rigid. They are conveyed to an ambient cooling system composed of multi-tiered belts with forced air circulation. Cookies must reach below 30 degrees Celsius before proceeding to filling. While the cookies cool, the peanut butter creme filling is produced in a separate, continuous emulsification system. The formulation includes icing sugar, hydrogenated vegetable oil, roasted peanut paste, salt, and emulsifiers such as mono and diglycerides. The ingredients are metered into a vacuum mixer fitted with high-speed rotating blades. The mixer maintains low pressure to prevent air incorporation, while the fat and sugar blend into a smooth paste. Product temperature is held between 38 degrees Celsius and 42 degrees Celsius to control viscosity and ensure deposit stability. The filling mass is pumped from the mixer into a stainless steel holding tank equipped with a slow agitator to maintain consistency. From there, the creme is fed through a positive displacement pump into a volumetric depositor that sits above the sandwiching conveyor. Cooled cookie halves are divided into bottom and top rows using a mechanical separator with indexed belts. The bottom halves are aligned and conveyed beneath the depositor. Each nozzle in the depositor corresponds to one cookie lane. As each cookie passes below, a metered quantity of peanut creme is dispensed onto the center of the bottom cookie surface. The deposit rate is synchronized with belt speed to maintain consistent fill weight and location. Top cookie pieces are then aligned with their corresponding filled bottom halves using a mechanical alignment rail. A pusher bar or servo-driven actuator lowers each top cookie onto the filling. The applied pressure is controlled to spread the filling to the desired diameter without squeezing it beyond the edge. The resulting sandwich maintains clean fill lines and full bonding across the contact surface. Assembled Nutter Butter sandwiches are conveyed through a short resting belt to allow any residual filling movement to stabilize. From there, they move into the packaging system. The first packaging stage consists of a flow wrapping machine fed by a timing belt that spaces cookies at fixed intervals. Wrapping film is unwound from large rolls and formed into a tube around the cookies using a forming collar. The longitudinal seam of the wrapper is sealed by heated crimp rollers, while the ends are cut and sealed by rotary jaws. Temperature and dwell time of the sealing jaws are set based on film thickness and line speed. The wrapped cookies exit the flow wrapper as individual units or twin packs depending on the product variant. Wrapped units are conveyed to a grouping system where multiple cookies are collected and inserted into multi-pack cartons. Mechanical pushers or robotic pick-and-place arms load the cookies into pre-glued cartons. Cartons are sealed using hot melt adhesive applied by contact nozzles. Glue setting is ensured by compression flaps and a short dwell section. The cartons are then labeled, coded, and discharged to case packing. Throughout the process, all movements are continuous and synchronized. Dough feed, forming, baking, cooling, creme preparation, depositing, sandwiching, and wrapping occur without manual intervention or batch holding. Each station is linked to upstream and downstream processes by belt conveyors, sensor arrays, and real-time control systems. The final texture of the Nutter Butter cookie shell depends on dough fat content, moisture level, forming pressure, and thermal profile. The filling spread and adhesion characteristics are governed by shear during mixing, fat phase structure, and filling temperature at deposition. The sandwiching step relies on timing and vertical alignment accuracy to avoid rotation or breakage. Rework is minimized through inline inspection at multiple points. Cookies with incomplete molding, overbake, off-center filling, or misalignment are removed by air rejection systems or diverted for grinding and remelting. Only fully conformed products proceed to final packaging. The design of the peanut shell shape is retained through rigid cavity molding, low dough expansion, and short baking time. Each cavity in the mold drum is precision machined to micron level tolerances. The emboss pattern depth controls final surface visibility. The moisture balance in the dough ensures sharp edge retention and minimal slumping during oven transit. The filling deposit pattern is a function of nozzle diameter, piston stroke length, deposit speed, and creme viscosity. The diameter of the final fill is determined by vertical pressure from the top cookie and the flow behavior of the fat matrix. The ratio between shell weight and filling weight is maintained within narrow limits to ensure structural integrity and mouthfeel. Line efficiency is governed by synchronization between forming rate, baking throughput, and filling capacity. Adjustments to belt speed, oven temperature, or depositor cycle timing propagate downstream. Any mismatch between stations can result in underbake, inconsistent fill, or packaging misfeeds. The mechanical layout of the Nutter Butter production line is linear and modular. Dough flows from mixer to molder. Biscuits flow from molder to oven. Creme flows from mixer to depositor. Sandwiches flow from depositor to wrapper. Each segment includes buffer zones to absorb variation and maintain steady output. Packaging formats can be switched by adjusting forming jaws, wrapping film feed width, and carton loader configuration. Line reconfiguration is managed through digital interfaces that adjust motion profiles, material flow paths, and spacing intervals. The final Nutter Butter product consists of 2 molded peanut-flavored cookies bonded with a central layer of smooth peanut butter creme. The top and bottom shells are symmetrical and embossed with the same pattern. The cream layer is centered and flush with the cookie edge. The finished unit exhibits uniform thickness, aligned sandwich halves, and sealed packaging with fixed weight. Each unit operation transforms the ingredients through shear, heat, pressure, cooling, or extrusion. No fermentation or chemical expansion occurs. All structural characteristics are mechanically imposed and thermally locked. The line operates at a continuous pace of thousands of cookies per hour. Consistency across units is maintained by regulating every input condition, from ingredient feed to forming pressure to deposit rate. All cookies follow the same linear path through the same physical conditions. The result is a uniform, mass-produced sandwich product with no variation in shape, weight, or filling distribution. The industrial process of bread production begins not with baking, but with an orchestrated balance of mechanics and chemistry, where every gram of input is measured, every rotation of a blade is timed, and every degree of heat is calculated long before the first loaf begins to take shape. The cycle starts in the mixing room, where automated ingredient handling systems transport vast quantities of flour through pneumatic conveyors, drawing it from silos positioned outside the facility and funneling it in clouds of fine white powder into stainless steel batch hoppers that feed into the primary dough mixers. These mixers, towering and gear-driven, don't simply stir. They press, fold, and stretch the mixture with rotating arms that mimic the pressure and pull of hands, but at a scale and speed no human could replicate. At the moment liquid meets dry, the system kicks into life, and the rhythm of kneading begins. Inside the mixing chamber, every second counts. The speed starts slow to allow hydration, gradually increasing as gluten strands form and interlace, building the elastic structure that will define the shape, rise, and texture of the finished bread. Temperature sensors within the dough track the frictional heat produced during mixing, while torque sensors monitor resistance to ensure the dough reaches a consistent development profile. Cooling jackets around the mixer basin activate if necessary, keeping the dough within its ideal thermal range to avoid overproofing later in the process. Once the target consistency and elasticity are reached, soft, slightly tacky, extensible, but resilient, the dough exits the mixer through a bottom hatch, sliding as one heavy, cohesive mass into the next stage. A sheeter receives the dough next. Twin rollers compress it into a continuous slab, which then moves through a series of gauges to ensure thickness and density remain exact. This is not a shaping step, it's preparation. The flattened dough is directed into a high-capacity divider where a series of volumetric pistons cut the slab into uniform portions. These pistons measure by volume rather than weight, ensuring that even as humidity or temperature fluctuates slightly, each piece contains the exact same mass of air and dough combined. Once divided, the pieces are dropped into intermediate proofers, tall, climate-controlled chambers where the dough rests in a carefully maintained environment of warmth and humidity. It's here that the dough begins to ferment actively for the first time. The yeast, having been activated during mixing, releases carbon dioxide, expanding the structure from within. But this step isn't about final rise. It's about conditioning the dough, allowing it to relax after the physical stress of division so it can be molded without tearing. After a set number of minutes, each portion travels via conveyor to the molder. A set of guide rollers gently flattens the dough again. Then curling belts begin to shape it, rolling the mass inward to form a tight spiral that will become the loaf's interior structure. Pressure plates calibrate tension precisely, ensuring the outer skin of the dough wraps around the inner layers tightly enough to support rise, but not so tight that the loaf bursts during baking. Once molded, the loaves drop gently into metal baking pans, moving along a wide belt. Each pan is pre-lubricated with a fine mist of oil dispensed by a jet spray system to ensure clean release after baking. At this point, the pans pass through the final proofer, a long, enclosed tunnel where heat and humidity are kept within strict boundaries. Here, the loaves experience their final rise, swelling as fermentation accelerates. The gases trapped in the dough expand, the gluten matrix stretches to accommodate the volume, and the surface tension pulls tight, smoothing the top into a rounded dome. Sensors along the proofer track height, spacing, and proofing time. Any variation is logged, and the system will adjust conveyor speed or proofer climate to compensate. If the dough rises too quickly, the texture becomes irregular. Too slowly, and the crust may blister or fail to color evenly. Timing here is crucial. Baking must happen at the peak of fermentation activity to lock in that volume. Once the proofing cycle finishes, the pans emerge from the chamber and feed directly into the oven. The industrial oven is a continuous tunnel design, divided into multiple thermal zones with independent top and bottom heat controls. As the pans enter, steam injectors release a high-pressure burst across the loaf tops. This initial moisture keeps the crust soft in the early minutes, allowing for maximum oven spring as the bread expands rapidly under intense heat. The steam also sets the crust structure and eventually contributes to its color and gloss. The baking process unfolds in stages. First comes expansion, where gases expand, alcohols evaporate, and enzymes break down residual sugars. Then comes gelatinization, as starches swell and set. Finally, Maillard reactions begin on the surface, turning the pale, supple dough into a rich, caramel-toned crust. The belt moves at a steady pace, calibrated so that by the time each loaf exits the last zone, it has reached the exact internal temperature required for complete bake, usually just over 96 degrees at the core. Exiting the oven, the loaves are hot and fragrant, but far too fragile for packaging. They roll forward on the conveyor and enter a spiral cooling system, a towering structure of coiled belts that winds upward, allowing the loaves to circulate through cooler air over the course of 30 to 40 minutes. Fans direct airflow from multiple angles, and vents above the line extract excess humidity to avoid condensation forming on the crust. As the temperature gradually drops, the crumb sets fully and moisture redistributes inside the loaf, ensuring softness remains throughout shelf life. Once cooled, the pans reach the depanning machine. A rotating arm, fitted with suction cups, lifts each loaf upward with precision timing, placing it onto a transfer belt while the empty pan continues onto a cleaning line. The pans are scrubbed with mechanical brushes, sprayed with sanitizer, and then dried by air knives before being stacked or returned to the molder for the next round. Meanwhile, the bare loaves now advance towards slicing and packaging. If the bread is destined for sale as whole loaves, it bypasses this stage, but most continue on to the slicer. This machine is built for speed. Multiple blades, mounted vertically in a row, oscillate at high speed as each loaf is pushed through by a belt-driven ram. The slices fall into alignment instantly, held together by guide rails as they move forward still in loaf shape. The next step is bagging. A plastic bag is blown open by a quick burst of air and guided into place by forming horns. The sliced loaf drops in, and a closing device, either a twist tie, tamper band, or plastic clip, seals the bag in one motion. An inline printer stamps each bag with a code indicating date, time, production line, and batch number. The sealed loaf is then guided onto a secondary conveyor for inspection. Cameras and weight sensors scan every packaged loaf. Any irregularities in size, shape, color, bag print, or closure are instantly flagged. Rejected loaves are diverted automatically, while the accepted product continues forward to be grouped for carton packing. Robotic arms pick up loaves in sets and stack them into shipping boxes, which are then sealed, labeled, and passed to the palletizer. The palletizing system uses multi-axis robotic arms to stack cartons onto wooden pallets in precise formations designed to prevent shifting or damage in transport. Slip sheets are placed between layers for stability. Once full, the pallet enters a stretch wrapper, where plastic film binds the load tight from base to top. A printed label is applied to the outer edge of the film, detailing product information, origin, destination, and tracking codes. Every action in this process is overseen by a centralized control network that connects mixers, dividers, molders, ovens, coolers, and packers into one coordinated line. Data flows constantly between stations. If the divider senses a shift in dough density, the molder adjusts tension. If the oven reports inconsistent browning, the slicer slows slightly to sync packaging output. Everything is in motion, yet everything is balanced. In a large-scale factory dedicated to the continuous assembly of sandwiches, every stage is a precisely engineered operation where timing, alignment, and consistency converge across hundreds of feet of synchronized machinery. And the process begins long before the first sandwich reaches the wrapper. It starts with bread loaves, already baked, cooled, and brought into the slicing system in racks, where they are automatically depanned, aligned, and fed into high-speed slicers fitted with ultra-sharp, serrated, or ultrasonic blades that oscillate thousands of times per second to deliver uniform, clean-edge slices without compressing the soft interior crumb or fracturing the crust. Once sliced, the bread slices travel by conveyor to a pre-alignment station, where camera-guided sensors and rotating guide arms ensure every slice is positioned in the exact orientation required for the next phase, which is the laying down of the base slices. These are distributed in pairs or rows, depending on whether the line is configured for single or multiple sandwich formats, and set evenly onto the moving belt with equal spacing between each set. The flow is constant, with no interruption between batches, and any variation in slice thickness or alignment is corrected in real time by pneumatic actuators and servo-driven guides that subtly adjust position and speed without halting the line. As the bottom slices approach the filling zones, the first application arrives in the form of spread, be it mayonnaise, mustard, aioli, butter, or any other emulsified or creamy base. A series of nozzles or roller spreaders applies a controlled layer, often using pulse pressure, to shoot a fan of spread across the surface, which is then evened out by a soft-tipped roller or oscillating blade to ensure consistent coverage all the way to the edges of the bread. Sensors mounted above each lane scan the surface to confirm the presence, distribution, and thickness of the spread. And if coverage falls below specification, a feedback loop either reapplies the layer or removes the sandwich from the line. After the base layer is applied, the sandwich moves into the protein zone. Here, pre-sliced meats such as turkey, ham, beef, chicken, or plant-based alternatives arrive from upstream feed systems, where they have been portioned, weighed, and fanned into stacks by centrifugal feeders or vibratory shakers. These stacks are lifted by robotic pick-and-place arms, equipped with vacuum suction or gripper fingers, depending on the product's texture, and laid gently onto each bread base with alignment controlled by high-speed imaging systems that adjust position in real time to match the orientation of the incoming slice. Every portion is weighed by inline check weighers before being applied, ensuring that each sandwich receives a uniform protein layer, with rejections happening instantly and automatically if tolerances are exceeded. Next comes the cheese layer, which moves from chilled stacks through a peeling and singulation system that separates individual slices, removes any protective film, and transfers them to a placement module. The cheese is picked and placed onto the meat with exact positioning, sometimes staggered depending on the sandwich style, and lightly pressed to ensure it conforms to the underlying surface without folding or hanging over the edge. The equipment adjusts for slice fragility using low-pressure vacuum heads and static control to prevent light cheeses from sticking to conveyors or deforming during placement. Vegetables come next, and this stage is often the most complex due to the variability in size, moisture, and fragility of the ingredients. Lettuce is dispensed from overhead hoppers with calibrated vibratory trays that gently shake shredded or leaf lettuce onto the sandwiches in measured volume, distributed evenly by spinning diffusers that sweep across the width of the belt. Tomatoes, cucumbers, and other sliced produce are fed from rotary magazines that release single slices in sequence, timed to the belt's movement, so each tomato lands directly at the center of the sandwich, guided by small airflow puffs or mechanical nudges if needed. Onion rings and other light layers are dispensed from spiral feeders or drop chutes, often with the assistance of static eliminators and light misting systems that prevent separation or clumping as the vegetables fall into place. If the top slice requires its own spread or condiment layer, a mirrored version of the first spreading station appears here, applying the layer just moments before the slice is joined to the assembled base. The top slice is picked by robotic arms from a secondary line of aligned bread slices, flipped if necessary depending on crust orientation, and gently pressed onto the assembled sandwich with just enough force to compress the stack into a unified structure without squeezing out fillings or deforming the shape. At this stage, the sandwich enters the compression and forming section. A series of soft rollers or belt presses applies uniform downward pressure to stabilize the build, enhance bite adhesion, and ensure the sandwich holds together through slicing, wrapping, and handling. The compression rollers are timed precisely to match belt speed, and the pressure profile is tuned to the product type, with more delicate sandwiches receiving lighter contact and denser builds compressed more firmly to lock the layers in place. Now fully assembled, the sandwich proceeds to the slicing station, where high-speed rotary or ultrasonic blades divide the product into the desired shape, typically halves or triangles. The slicing system is mounted on actuators that follow the motion of the sandwich as it moves along the belt, ensuring the blade enters and exits the loaf cleanly without tearing or pulling. Blade tension, sharpness, and angle are maintained through automated diagnostics, and the entire slicing module is flushed and sanitized between shifts to prevent cross-contamination. Cut sandwiches are now directed into the inspection lane, where overhead cameras and weight sensors verify slice alignment, edge definition, symmetry, and overall appearance. If a sandwich is misaligned, overfilled, underweight, or damaged during slicing, it is ejected by air blast or mechanical diverter before it reaches the wrapping system. The accepted sandwiches pass into the packaging zone, where the method of wrapping depends on the product's end use. For flow-wrapped sandwiches, the product enters a film feed tunnel where printed plastic film is drawn over and around the sandwich by guide belts, sealed along the back and ends by heated jaws that press and crimp the film closed in less than a second. A date coder prints production information onto the film surface just before the end seal. For chilled sandwiches sold in wedges or clamshells, the product is inserted by pick-and-place units into pre-formed rigid plastic containers. The lid is pressed or snapped into place and sealed with adhesive label strips or heat-sealed foil, depending on product design. Transparent sections are aligned with the sandwich face to ensure maximum visibility on shelf. Once wrapped, the sandwiches are grouped for boxing. A case packer counts the products and loads them into corrugated cartons, aligning each stack for minimal movement during shipping. Cartons are formed automatically from flat blanks fed into a forming station, sealed with hot melt glue or folded tabs, and labeled on the fly with barcodes, lot numbers, and shipping data. Each carton is scanned and weighed, and any deviation is flagged for inspection. The approved boxes move to the palletizing cell, where robotic arms stack them onto wooden or plastic pallets with layer patterns designed to balance weight and prevent shifting. The pallets are then rotated through a stretch wrapping station where film is applied under tension from bottom to top, stabilizing the entire load for transport. A final label is printed and applied to the side of the pallet with a scanner-readable code containing the production batch, shift, line number, and timestamp. Bagel production at factory scale is a continuous ballet of movement and transformation, where the dense, chewy character of each finished product is the result of precisely sequenced operations carried out by synchronized machines, each tuned to interact with dough in a way that preserves its integrity, develops its structure, and creates the exact conditions required for that unmistakable crust and crumb. It all begins in the dough room, where flour moves from towering silos into enclosed conveyor tubes, descending by weight into a batcher that draws measured volumes of water, salt solution, yeast suspension, and additional agents through chilled, jacketed feed lines that maintain temperature consistency from the first pump to the final discharge into the mixer. As the ingredients come together in a high-capacity spiral mixer, the arms begin turning slowly, cutting through the thickening mass with powerful, spiraling force, pulling the flour into the water and folding the developing dough inward from all angles. Unlike lighter breads, bagel dough requires far more resistance and strength, so the machines are set to operate under heavier torque, and the texture is intentionally firmer from the start. Temperature probes track internal friction heat. If the dough rises beyond the target, a cooling system kicks in, circulating chilled water through the ball's outer jacket, allowing the dough to strengthen and ferment without overheating. The mixing continues until the dough becomes tight, elastic, and resilient to touch, ready not for shaping, but for division. At this point, the dense dough is released through a bottom hatch and fed directly into a portioning unit that slices it into thick, consistent strips, each one calibrated for weight and volume by servo-guided sensors that track the length, width, and compression of the dough strand as it moves forward on the belt. These portions are then carried forward to the bagel former, a specialized system unique to this category of baked goods. Here, each dough piece is rolled into a rope between two textured conveyor belts, gradually tapering the ends for seamless closure. The ropes are then transferred to the forming drum, a rotating cylinder fitted with a center plunger and an outer ring guide that picks up the rope, curls it into a circle, and presses the ends together into a seamless loop without pinching, tearing, or folding. Formed bagels are deposited onto a wide, dusted conveyor belt, each one spaced perfectly from the next by indexing arms that keep rows uniform as they head toward the proofing section. At this stage, the dough is still dense and compact and needs controlled time to relax and ferment before any further processing. The trays of raw bagels enter an enclosed, temperature and humidity regulated proofer where warm, moist air surrounds the dough, gently encouraging expansion without aggressive rise. Over the next 15 to 20 minutes, the yeast becomes active, releasing carbon dioxide and creating a subtle softness beneath the taut exterior. Proofing times are controlled to the minute, with sensors tracking volume gain and relative humidity in every lane of the chamber, so that every bagel arrives at the next step with the same bounce, shape, and tension. What follows is the defining characteristic of bagel production: boiling, or more accurately, a high-temperature water bath that sets the outer crust before baking begins. As the proofed bagels exit the chamber, they move onto a boiling belt that carries them through a long stainless steel trough filled with circulating water, often mixed with barley malt or a similar solution to enhance browning later in the oven. The bagels float as they enter, and a set of rotating paddles gently submerge each one to ensure even exposure. They spend only seconds in this bath, but it's enough to gelatinize the starches on the surface, locking in shape and creating the foundation for that dense, glossy crust. Once boiled, the bagels are lifted from the water by an upward sloping mesh belt and allowed to drain momentarily before entering the topping section, where optional finishes, sesame, poppy, onion, salt, are applied. This happens through a combination of timing, moisture, and gravity. The wet surface of each bagel acts as a natural adhesive, so as they pass under overhead hoppers or through rotary topping applicators, the seeds or seasonings fall onto the dough and stick cleanly to the surface. Excess toppings are collected by a vibrating reclaim system beneath the belt, filtered and returned to the hopper for reuse, ensuring nothing is wasted and every bagel receives an even coating. The topping section leads directly into the oven, a massive tunnel-style system divided into multiple thermal zones that gradually bring the bagels from boiled to baked over the course of 10 to 12 minutes. The first zone introduces radiant heat to activate oven spring, but because the crust is already partially set, expansion is modest and the shape remains tight and uniform. In the middle zone, the crust begins to brown, driven by Maillard reactions that create the deep caramel tones and toasty aroma typical of well-baked bagels. The final zone balances color and internal moisture, holding a slightly lower heat to allow the core temperature to rise without burning the toppings. Throughout the bake, airflow is precisely directed and humidity is adjusted by steam injection valves to control crust thickness and finish. As they exit the oven, the bagels are fully formed, firm to the touch, richly colored, with a light sheen from the boiling stage and a tightly structured crumb inside. But at this point, they're still over 90 degrees Celsius internally and too hot for packaging, so the belt carries them into a spiral, cooling tower, a towering column of coiled belt that winds upward, allowing each bagel to travel along a rising path while being cooled by ambient air and filtered ventilation. Over the next 20 to 30 minutes, the internal temperature drops steadily and the crust stabilizes, preventing condensation and preserving the chewy exterior texture. From the base of the spiral, bagels are sorted by product type: plain, topped, seeded, and diverted into corresponding packaging lanes. If they are to be sold whole, they continue uncut, passing through alignment rails and into flow wrapping tunnels, where printed film encloses them in a tight, sealed wrap that's closed by heat-sealed seams on the underside. For multi-packs, bagels are counted and stacked automatically, transferred into trays or bags using pneumatic plungers or robotic suction heads, and sealed with clips, twist ties, or tamper-proof labels. Batch codes, production times, and expiration dates are printed by inline thermal inkjet systems on the package surface. If the bagels are destined for pre-sliced use, they proceed to the slicing unit, where a high-speed circular blade, often with ultrasonic vibration, cuts horizontally through each bagel's midpoint, while the product is held firmly in a compression cradle that prevents movement or tear out. The two halves remain paired and are then rewrapped as a sliced unit, ready for sandwich use or toasting. The sliced bagels are also inspected by weight, diameter, and color, with overhead cameras tracking any deviation in cut depth or alignment and removing out-of-spec product instantly from the conveyor. From there, the finished and packaged bagels are transferred into carton loading stations. A mechanical arm stacks them into pre-formed boxes, which are then sealed, labeled, and conveyed to the palletizing zone. Here, a robotic palletizer organizes the cartons in tight formations, applying slip sheets between layers and wrapping each pallet in film to protect it during transport. Each pallet is labeled with a scannable tracking code that contains all relevant production data: time, line, operator, batch, and destination. Throughout this entire process, every machine, every transfer, and every transformation is governed by a central control system that monitors line speed, batch integrity, ingredient flow, humidity, oven temperature, belt timing, and packaging rates. Adjustments happen automatically. If the boiling water cools by 2 degrees, the belt speed slows. If the oven heat drifts too high in zone 3, airflow is redirected. If the topping adhesion falls below threshold, an alert is triggered, and the hopper motor pulses slightly to shake more seed onto the line. Nothing here is guesswork. Everything is calculated. Bagels don't just bake. They're shaped, built, boiled, and finished by systems that never stop watching, adjusting, and maintaining perfect rhythm. The machines don't work alone, but in coordinated layers, each one tuned to preserve the dense structure, glossy crust, and unmistakable bite that defines a factory-made bagel. In just over an hour, a lump of flour and water is transformed into something firm, chewy, finished, and sealed, ready to ship, ready to slice, ready to toast, and repeated thousands of times per hour without pause. Spam canned meat begins its manufacturing process with chilled pork cuts entering the initial reduction line, where rotating blade assemblies slice the dense blocks into manageable segments that can feed smoothly into the primary grinder. The grinder's helical screw immediately draws these pieces forward, pressing them through a precision-drilled plate that creates uniform meat particles. And this uniformity allows the next mixing stage to distribute additives consistently. These freshly ground particles move directly into a temperature-controlled mixing chamber, whose jacketed walls circulate coolant to maintain a low and stable temperature, ensuring that the proteins do not smear or break down during agitation. As the ground meat settles inside the chamber, automated ingredient dispensers positioned above it release a measured sequence of salt, curing elements, sugar, and additional stabilizing agents, and the moment these ingredients fall in, a pair of interlocked ribbon paddles begins a slow, synchronized rotation designed to pull material from the outer walls toward the center. This inward folding pattern repeats continuously, which gradually builds a uniform matrix of meat and dissolved additives, and that uniform matrix prepares the mixture for vacuum treatment. Once the system's sensors detect that mixing torque has stabilized, an indicator of proper consistency, the vacuum lid seals over the chamber and the air extraction pump begins lowering internal pressure. As the pressure drops, microscopic bubbles rise from the paste and collapse on the surface, and this removal of trapped gases compacts the mixture into a dense, cohesive phase that will later hold its shape inside the can. When the vacuum cycle completes, hydraulic actuators tilt the entire mixing vessel forward, guiding the meat paste toward a stainless steel discharge chute. This chute leads the paste directly onto an enclosed transfer conveyor whose internal airflow is tightly controlled. And this enclosure prevents temperature fluctuations as the paste moves toward the portioning system. As the conveyor delivers the mixture into the depositor's intake manifold, a series of metering cylinders opens to receive it, each cylinder equipped with a sliding gate and a vertically driven piston. These cylinders fill one after another until integrated load cells confirm that each chamber holds the exact programmed mass, and once this mass is reached, the sliding gates close to isolate the measured portions. Meanwhile, empty cans advance along a parallel conveyor that narrows into single-file alignment, and as they move, they pass through filtered air jets that clear their interiors of loose dust or microscopic particles. This preparation ensures that when the cans reach the filling zone, each one is ready to receive its measured charge of meat paste without interference. The two conveyors meet at the depositor, where each can is precisely positioned beneath a cylinder's outlet by a mechanical indexing arm that pushes the cans into perfectly spaced pockets along the line. As soon as a can reaches the correct location, the piston above it begins its downward motion, forcing the compact meat paste into the metal cavity in a single continuous stroke, which eliminates voids and establishes the characteristic block-like internal structure. When the piston retracts, a fixed wiper blade scrapes the cylinder's interior surface to prevent residue buildup, and this ensures that every subsequent portion enters the next can with the same exact mass and texture. Once filled, the cans transition onto a settling conveyor equipped with a low-frequency vibration plate. This plate applies gentle vertical oscillations to the freshly filled cans, allowing the paste to settle and eliminate microscopic gaps that may still remain after piston filling, and the stabilized contents prepare the cans for immediate sealing. As the cans leave the settling area, they enter a high-speed seaming machine, where a preformed metal lid is dropped precisely onto each rim, while a rotating chuck and roller assembly crimps the lid's edge into the can body. This forming operation creates a gas-tight double seam, and the uniformity of this seam is essential for the next major phase, thermal processing. Once sealed, the cans enter a continuous retort system, a long, tunnel-like chamber where steam or superheated water circulates around rotating baskets that hold the cans. As the baskets move, every can experiences consistent heating, and this heat penetrates the dense meat block, activating the curing reactions and stabilizing the proteins while rendering the final texture. The retort maintains precise time and temperature conditions so that each can reaches the target internal temperature at the correct rate. And this controlled heating transforms the formerly soft paste into the firm, sliceable form associated with the product. When the thermal cycle ends, the cans exit the retort and immediately enter a cooling zone where chilled water sprays reduce their temperature in stages, preventing sudden contraction that could deform the seam. After cooling, the cans move onto an air drying conveyor, where high-velocity fans remove surface moisture to prepare them for labeling. The dry cans then enter the labeling carousel, which applies adhesive-backed wraps that align perfectly using optical registration sensors, ensuring each label sits squarely against the cylindrical surface, without wrinkles. As the labeled cans rotate through the carousel, pressure rollers press the labels firmly to guarantee complete adhesion and a smooth exterior finish. Once labeling is complete, the cans advance toward the inkjet coating station. Here, a high-resolution nozzle prints alphanumeric production information onto the top or bottom surface of each can. The printer synchronizes its spray pulses with the conveyor's exact speed so each code lands consistently in the same position. Immediately after printing, a short section of forced air nozzles dries the ink before the cans make contact with any guiding rails, preventing smudging during the remainder of the line. With coating complete, the cans reach the final inspection conveyor. A series of sensors check seam integrity, label placement, fill height, estimated through weight readings, and can dimensions. Any can falling outside the allowed tolerance triggers an automated pusher arm that diverts it from the main flow. The accepted cans continue onward to the packaging assembly, where they enter a carton forming machine. This machine erects flat cardboard blanks into open cartons using vacuum grippers and folding rails. And once the cartons hold their shape, the cans slide into them in tightly organized rows. As the cartons fill, an overhead flap folder closes the top panels while a gluing station applies a thin line of adhesive. Compression belts then squeeze the cartons briefly to activate the bond. The sealed cartons immediately transition to a palletizing system. This system arranges the cartons layer by layer onto large pallets using a pattern that maximizes vertical stability during transport, and each layer aligns precisely with the next through mechanical guides that keep the arrangement square. Once the pallet reaches its programmed height, a wrapping arm encircles it with stretch film, stabilizing the entire load for movement. The finished, fully wrapped pallets then roll onto the outbound conveyor, completing the transformation from raw pork cuts to fully processed, thermally stabilized, sealed, labeled, coated, and packed canned meat. Smoked salmon begins its manufacturing process with whole chilled fillets entering the trimming line, where a synchronized set of blade assemblies removes the thin belly membrane and levels the surface of each fillet to create a consistent starting geometry. This geometry is crucial because it determines how evenly the salt mixture will absorb later. So immediately after trimming, the fillets slide onto a conveyor that positions them for the pinbone extraction machine. Here, a series of narrow oscillating grippers aligns over the muscle surface, gripping and lifting each pin bone in a single upward pull. This extraction eliminates hard points that could interrupt the uniform curing and slicing process downstream. Once trimmed and deboned, the fillets enter the curing section. A volumetric salt dispenser releases measured layers of salt and sugar over the conveyor belt, and the fillets pass beneath its nozzles, so each surface receives an exact dosage. As soon as the salt mixture makes contact, a mechanical arm flips each fillet to coat the opposite side, ensuring symmetrical curing. The salt crystals immediately begin drawing moisture from the muscle fibers, and this moisture migrates toward the surface, dissolving the crystals into a brine layer. To control this reaction, the fillets move into a stacked curing tunnel. In this tunnel, multiple perforated trays hold rows of fillets while a constant airflow passes over them. This airflow pulls excess moisture away and maintains a stable environment, allowing the muscle proteins to tighten and form the firm, translucent texture associated with smoked salmon. As curing progresses, the brine that forms on each fillet drains into collection channels beneath the trays. These channels lead to a filtration chamber where the liquid's density and conductivity are measured. Although the brine is discarded, the sensor data ensures that each batch reaches a consistent cure level before exiting the tunnel. When the curing cycle finishes, the trays slide onto an outbound lift that lowers them to the rinsing line. Here, a set of low-pressure water jets washes the residual surface salt from the fillets without disrupting the internal gradient created during curing. The water jets oscillate side to side, covering every region of each fillet. After rinsing, the fillets pass through an air knife dryer, where high-velocity sheets of air remove excess surface moisture and prepare the flesh for the drying stage. The dried fillets enter a dehydration chamber equipped with long horizontal racks that move forward in slow increments. Within the chamber, controlled heat and airflow create a narrow humidity band that gently reduces water activity. This step tightens the muscle structure even further, which allows smoke particles to adhere more effectively later. As the fillets travel through the chamber, internal moisture equalizes from center to exterior. By the time they exit, each fillet has reached the ideal pre-smoking firmness. Immediately after dehydration, the fillets pass into the smoking system. This system is a multi-zone chamber divided into sections that control smoke density, airflow direction, and temperature independently. The first zone introduces a thin, mild smoke created by controlled smoldering of hardwood chips inside a sealed generator. The smoke enters through overhead ducts and spreads evenly across all racks. As the fillets move forward, they encounter the second zone, where smoke density increases and recirculating fans push air diagonally across the racks to ensure complete surface exposure. Temperature remains low, so the flesh does not cook. Instead, the smoke compounds slowly bind to the proteins, forming the glossy outer layer characteristic of smoked salmon. The final smoking zone shifts airflow to a vertical pattern. Fans pull smoke downward across the fish, penetrating any microgrooves in the muscle surface. The chamber's sensors track particulate levels continuously, adjusting feed rates so each batch receives consistent exposure. By the time the fillets exit the smoking chamber, they exhibit a uniform color gradient and a stabilized texture that can withstand mechanical slicing. The smoked fillets then travel to a brief cooling tunnel, where chilled air circulates around them to halt further smoke absorption. The cooling also firms the muscle, which enables cleaner cuts in the slicing stage. As each fillet cools, it is transferred onto a wide conveyor that feeds into the slicing preparation unit. This unit aligns fillets lengthwise using adjustable side guides. Once aligned, an overhead scanner maps the fillet's dimensions, determining thickness variations that could influence slicing pressure. With dimensional data collected, the fillets advance toward the horizontal slicer. This machine uses a rapidly vibrating blade or multi-blade band system that creates thin, even slices with minimal pressure. The oscillation speed keeps the blade from dragging through the flesh, producing smooth surfaces. As the blade moves, each slice falls gently onto a receiving belt positioned below the fillet. This belt is coated with a non-stick surface, so slices do not fold or stretch. A secondary belt intersects at a shallow angle and transfers the slices in a neatly fanned arrangement. This arrangement maximizes visibility and uniformity for packaging. Once sliced, the salmon enters the portioning zone. Laser-guided weigh cells determine how many slices make up the programmed portion weight, and conveyor actuators separate the slices into exact groups. These portions move forward onto chilled stainless steel plates that stabilize the slices while the vacuum packager prepares the film. Above the plates, a sheet of high barrier film unwinds between two tension-controlled rollers, maintaining consistent thickness and preventing wrinkles. The plates then slide beneath the film, and the chamber closes over them. Inside the vacuum packager, air is extracted from the sealed chamber, causing the film to drape tightly over the salmon slices. Once vacuum reaches the set value, a sealing bar applies heat around the pack's perimeter, bonding the film to the lower tray. The chamber then releases, and the packages exit onto a cooling conveyor, where cold air vents help the sealed film re-harden and maintain shape. After cooling, the packages move beneath a printer that adds production codes and traceable identifiers in a uniform location. With coding complete, the packages travel through an inspection array. Multiple sensors evaluate seal integrity by measuring how the film reflects laser light. If any section deviates from the expected pattern, the system flags the package and removes it from the line. The remaining packages continue toward the cartoning machine. This machine erects cardboard sleeves and inserts the sealed packs into them using sliding rails. The sleeves close around the packs, forming rigid, stackable units. The carton packs then advance to a shrink-wrapping tunnel. Here, a thin layer of polymer film forms a tight secondary wrap around multiple cartons at once, stabilizing them for palletizing. The film shrinks under warm air jets and contracts uniformly around the load. Next, the stabilized multi-packs reach the palletizer, where mechanical arms lower each group into a structured pattern on a pallet deck. Once enough layers accumulate, a rotating arm dispenses stretch film to lock the full pallet together. Returning to the earlier stages, the process can be understood as a continuous sequence where each transformation prepares the salmon for the next. For example, the trimming ensures clean edges that allow salt to contact evenly. The curing step modifies water distribution across the flesh, increasing firmness so the fillets can tolerate the dehydration chamber's airflow without warping. Dehydration, in turn, creates a surface environment ideal for smoke absorption. Smoke exposure produces a protective exterior that both contributes flavor and stabilizes the fillet for slicing. That stabilized texture then enables the slicing blades to glide without tearing, producing aesthetically consistent pieces. Packaging locks in these qualities by removing oxygen and sealing moisture, and the final palletizing step ensures the product remains structurally stable during distribution. Each component in this chain depends on the previous one functioning precisely. For instance, the air knife dryer, before dehydration, removes free water that would otherwise block smoke adhesion. The scanner before slicing collects geometric data that allows the slicer to adjust blade angle and oscillation speed. The laser seal inspection verifies that vacuum packaged trays maintain internal negative pressure, preventing unwanted changes to texture. Even transitions between steps contribute to consistency. Conveyors connecting curing, rinsing, drying, smoking, and slicing maintain uniform spacing and synchronized speed so fillets never bunch or overlap. In the smoking system, airflow patterns shift gradually, ensuring that smoke density changes do not shock the fillets and cause uneven absorption. Cooling tunnels introduce chill in stage temperature bands, preventing rapid contraction of the smoked flesh. Further upstream, the curing tunnel's brine drainage pattern ensures that salt contacts both sides of each fillet evenly over time. The perforated trays allow moisture to escape uniformly, reducing pooling that could disrupt the curing gradient. Downstream, The slicing portioner uses real-time weight calculations to maintain consistent package weights, even if individual slices vary slightly in thickness, due to natural variations in the fillet. Finally, each process concludes by stabilizing what the previous one created. Curing stabilizes moisture, drying stabilizes texture, smoking stabilizes the exterior protein structure, cooling stabilizes slice quality, and vacuum packaging stabilizes the final product against environmental changes. Chicken breasts begin their manufacturing process as chilled, whole muscle portions move from bulk bins onto the initial alignment conveyor, where parallel guide rails orient each piece in the same direction to prepare them for precision trimming. The trimming machine uses a series of synchronized rotary blades that contour along the natural shape of the breast, removing residual skin, excess fat, or uneven edges, so the muscle presents a consistent thickness for all downstream steps. As each trimmed piece leaves the blade assembly, it transitions onto a weigh belt, whose integrated load cells capture mass data in real time, allowing the system to sort the breasts toward different processing paths based on their size profile. Once sorted, the chicken breasts advance to the surface inspection module. Overhead, scanners emit a structured pattern of light that maps each fillet's geometry, measuring thickness, curvature, and moisture sheen. The resulting data determines how the fillets will be oriented for the tenderization stage. The conveyor adjusts its speed to ensure spacing between fillets, keeping each breast centered beneath the next mechanical unit. When a fillet reaches the tenderizer, two opposing roller heads covered with evenly spaced protrusions lightly compress the muscle fibers. This compression standardizes texture and promotes even absorption during subsequent marination. Directly after tenderization, the breasts enter the injection system. Here, a horizontally oriented manifold holds dozens of thin, hollow needles aligned in a grid pattern. As the fillets pass beneath them, the conveyor pauses momentarily while the needles descend into the muscle. Pressurized pumps deliver a calibrated solution, often containing water, salt, and functional ingredients, through the needles into the interior of each breast. The injection system monitors internal pressure to prevent overfilling and ensures that the distribution remains uniform throughout the muscle. When the needles retract, the conveyor restarts and sends the breast toward the tumbling drums. The tumbling drums rotate slowly around a horizontal axis, their interior surfaces lined with lifting baffles that scoop and drop the chicken repeatedly. This tumbling motion distributes the injected solution evenly and allows the muscle fibers to relax, improving texture. The drums operate under vacuum, removing trapped air from between muscle layers and enhancing the efficiency of the tumbling action. As the drum completes its cycle, a discharge door opens and the breasts slide onto a perforated conveyor where excess liquid drains away before the next processing stage. Following tumbling, the breasts enter a flattening system designed to create uniforms, thickness across all pieces. Two parallel belts run through a narrowing gap, pressing each breast gently but firmly as it passes. Sensors above and below the belts measure compression force and automatically adjust the belt spacing. This guarantees a uniform surface thickness, which will later allow consistent thermal processing and slicing if required. Once flattened, the fillets move towards the portioning unit. The portioner uses a combination of vision scanning and dual blade cutters to segment each breast into precise shapes or weights, depending on the intended final product. For example, a large breast may be divided into multiple uniform cutlets. The scanning system builds a 3D model of each fillet's profile, determining the optimal cutting lines for maximum yield. Rotary blades then execute each cut, while the fillet is kept motionless by a short vacuum hold on the conveyor. The cut pieces drop onto a secondary belt that organizes them into rows for further processing. At this point, the breasts may undergo surface seasoning. A dry ingredient applicator deposits an even curtain of powdered seasoning across the conveyor. The fillets pass beneath the curtain, where the powder adheres to the slightly tacky surface left from the tumbling process. A vibrating platform beneath the belt helps distribute the seasoning uniformly, preventing clumping. An air knife station then removes excess particles, ensuring consistent coverage. Next, the breasts enter the forming and shaping line. This system uses a high-pressure forming chamber to shape pieces into standardized contours if the product requires precise geometry. The breasts slide into molding cavities created inside a chilled forming plate, and a top plate descends to apply uniform pressure. The muscle conforms to the cavity shape, and after a brief hold, the mold opens, pushing the shaped portions onto a release belt. This shaping improves the predictability of cooking and slicing patterns later. From shaping, the chicken breasts move toward the thermal treatment area. The first step is preheating, where the fillets pass through a controlled warm air tunnel that brings their surface temperature to a precise range. This prevents shock when they enter the main cooking chamber. The preheated breasts continue onto a multi-zone oven with separate temperature and airflow controls. The first zone rapidly increases internal temperature through forced convection. The second zone stabilizes the temperature rise to prevent overcooking on the exterior. The third zone holds the chicken at its target core temperature long enough to achieve structural firmness. Inline temperature probes mounted on robotically positioned arms insert into sample breasts at intervals to verify that the oven settings align with the internal heating model. These probes transmit data instantly to the oven's control module, which adjusts airflow, humidity, and heat output to ensure uniformity across the entire batch. As the cooked breasts exit the oven, they enter a rapid cooling tunnel where chilled air streams across both sides of the fillets to lower their temperature quickly, locking in texture and preventing residual cooking. If the product requires slicing, the cooled breasts drop onto the slicing conveyor. A high-speed blade assembly cycles through several thousand oscillations per minute, producing clean cuts with minimal pressure. The slicing unit uses sensors to map each breast surface and adjust blade angle to maintain consistent thickness across every slice. As slices fall onto the belt below, they arrange automatically into overlapping shingled patterns using a series of angled guide plates. This pattern makes packaging easier and ensures visual uniformity. If the product remains whole, the breasts bypass the slicer and continue toward the surface freezer. This system uses extremely cold air circulated at high velocity to chill the outer layer of each fillet just enough to stabilize its shape. This process, known as crust freezing, prevents deformation during packaging and helps maintain the precision of portions created earlier. Once properly cooled or crust frozen, the breasts enter the packaging line. Here, they move into a vacuum sealing machine equipped with multiple forming pockets. Each pocket holds a single breast or sliced portion. The bottom film pulls tightly into the pocket to create a tray-like shape, and the chicken breast settles into this molded film. A top film then drapes over the product, and the chamber closes. Air extraction creates a vacuum that tightens the film around the product. A heat seal bar bonds the edges of the film layers, locking the product inside an oxygen-reduced environment that preserves texture. After sealing, the packages travel along a cooling belt to allow the film to contract evenly. The next station is the print coder, where inkjet nozzles apply product information and production identifiers onto each package. Optical sensors verify print legibility and alignment. Packages with misprints are diverted by a pneumatic pusher arm that only activates for items exceeding the coded tolerance. The accepted packages then move into the inspection unit. X-ray scanners evaluate internal density to identify bones or foreign matter. Because chicken breasts vary naturally in density, the scanner uses an adaptive algorithm tuned to muscle structure. Any package showing an anomaly is removed automatically. Approved packages proceed toward the carton loader. The carton loader erects flat cardboard blanks into open containers using mechanical folding arms. The vacuum-packed chicken slides into these cartons via a sloped feeding chute, and adhesive applicators seal the top flaps. The cartons then pass through a bundling station where they group into sets. A shrink-wrap film encircles these groups, and they enter a heat tunnel where warm air shrinks the film tightly around them. Once bundled, the cartons advance toward palletization. A robotic arm lifts each bundle and places it onto a pallet following a precise stacking pattern optimized for stability. Layer by layer, the stack grows until it reaches the programmed height. When complete, an automated stretch wrapper encircles the entire pallet with a spiraling sheet of film that secures the load. The process for Haribo gummy bears starts in the dissolving room, where glucose syrup and granulated sugar are pumped and conveyed into a heated stainless steel vessel. This vessel, fitted with high-speed agitators and a triple-wall steam jacket, maintains constant agitation while heating the syrup mixture to around 110 degree cup walks. The goal is to dissolve the sugar completely and create a smooth, viscous base. Flow meters and density sensors monitor the syrup's solids content and concentration in real time. Once dissolved, the hot sugar solution is pumped into a vacuum cooking chamber. Here, under reduced pressure, the solution is further concentrated and residual moisture is removed. The vacuum environment allows water to evaporate at lower temperatures, preserving the integrity of thermally sensitive ingredients like flavorings and gelatin to be added later. The cooked syrup exits the vacuum chamber at a high Brix level, typically 78 or 80% solids. Gelatin, a key component of gummy bear texture, is processed separately. It is first weighed and hydrated in a pre-mixing tank, where it soaks in cold water under gentle agitation for several hours. This allows the gelatin to swell and dissolve fully. Once hydrated, the gelatin slurry is gently warmed to 60-70 degrees Celsius and held in a circulation loop to maintain its viscosity and flow properties. Agitation is constant but low shear, preserving the molecular structure essential for the signature gummy chew. The concentrated sugar glucose syrup and the liquefied gelatin are metered into a dynamic mixing vessel. In this unit, the two streams are blended under vacuum to prevent air bubbles. Inline emulsifiers introduce fruit juice concentrates, plant-based colorants, citric or malic acid, and flavor oils. These are injected at precise intervals using servo-controlled diaphragm pumps. Optical clarity, pH, viscosity, and temperature are continuously monitored and regulated. The entire mixture forms a uniform candy mass with a temperature between 75 degrees Celsius and 85 degrees Celsius. To create multiple flavor variants, the unified base is split into smaller batches and pumped into separate flavor ash color blending tanks. Each tank is dosed with its assigned fruit flavor and colorant: strawberry, lemon, orange, raspberry, apple, pineapple, each controlled by automated recipe software. Once blended, each colored candy mass is held in jacketed kettles that maintain temperature and prevent settling. The molded shaping process begins with starch preparation. Cornstarch trays, shallow wooden or plastic frames filled with fine cornstarch, are first leveled and dried. These trays pass under a starch molding board fitted with multiple metal stampers shaped like gummy bears. The stampers press into the starch, leaving behind thousands of negative impressions. The flavored candy mass is deposited into these starch impressions by a multi-head depositor. This machine uses pneumatic or servo-driven nozzles to fill each cavity with a precise volume of hot liquid candy. Each nozzle is temperature controlled to maintain candy flow without crystallization or gelation. The depositor can move in synchronized XY motion, matching the layout of cavities in the starch bed. Depositing speed exceeds several hundred rows per minute. Once filled, the trays are conveyed into a controlled environment curing room. Here, over a period of 24 to 72 hours, the gummy candy sets and matures. During this time, the gelatin network fully develops, moisture migrates, and the candy reaches its final elasticity. Room conditions are tightly regulated, typically at 20 to 25 degrees, with 15 to 25% relative humidity. Airflow is carefully balanced to avoid uneven drying, and trays are rotated periodically. After curing, the gummy bears are removed from the starch using a tray inversion system. Trays are flipped onto a vibrating sieve table, and the bears fall free from the starch. Remaining starch is separated via vibration and aspiration, and returned to the starch storage system for drying and reuse. The gummy bears are now fully formed, but covered in a thin layer of starch dust. The bears enter the cleaning stage. First, they are conveyed through a rotary drum fitted with soft brushes and low-pressure air jets to remove starch residue. Next, they are transferred into an oiler drum. Here, the gummies tumble slowly while being misted with a thin layer of food-grade oil, such as carnauba wax or mineral oil. This coating gives them their glossy appearance, prevents sticking, and enhances mouthfeel. Rotation speed and spray intensity are precisely regulated to ensure uniform coverage. Polished gummy bears exit the oiler and are conveyed into an optical sorting system. High-resolution cameras scan each piece for size, shape, and surface defects. Bears that are deformed, broken, or discolored are identified by the vision system and removed by high-speed air nozzles. Approved pieces continue to the packaging line. Packaging is determined by product format: stand-up pouches, pillow bags, tubes, or bulk boxes. The cleaned gummy bears are weighed or counted using multi-head weighers that drop exact quantities into form-fill seal machines. These machines unwind printed plastic film, form it into bags, fill the bags with candy, and seal the top and bottom using heat-sealing jaws. Bag weights are controlled within +1 gram tolerance. Excess weight is trimmed in real time by the Wayfiller interface. Each package receives a date code, lot number, and barcode through an inkjet or laser coder. Vision systems verify the print quality, placement, and code accuracy. Improperly coded bags are automatically rejected. Finished bags are grouped by format and quantity and sent to secondary packaging. Secondary packaging uses automatic case erectors to form cardboard boxes. Robots or pneumatic arms load bags into the cases according to a stacking algorithm. Once filled, cases are sealed with hot melt glue or tape and printed with case-level traceability information. At the palletizing station, cases are stacked in predetermined patterns by robotic arms equipped with suction pads or mechanical grippers. Slip sheets are inserted to stabilize each layer. Full pallets are stretch-wrapped with tension-regulated plastic film and labeled with shipping data, including batch codes and destination tags. All stages of production are governed by programmable logic controllers. Each machine, from dissolver to depositor, oiler to packer, communicates with the central control system through industrial Ethernet. SCADA systems display real-time data, including syrup concentration, starch temperature, mold fill rate, curing status, polishing speed, and packaging counts. Environmental controls are maintained throughout. In the curing room, air handling systems monitor and adjust temperature and humidity minute by minute. In the packaging area, overpressure systems keep air clean and filtered. In mixing rooms, positive pressure and stainless steel surfaces ensure hygiene. Every equipment contact surface is food grade and cleaned using clean-in-place cycles or automated CIP skids. Hot detergent and sanitizing solution are circulated through tanks, pumps, and pipes on a scheduled cycle. verified by conductivity sensors and time logging. Ingredient traceability is enforced by barcode and RFID scanning at every stage. From glucose syrup intake to final packaging, every lot is digitally recorded and linked to each production batch. Quality control samples are pulled at each phase: post-mixing, post-curing, post-cleaning, and post-packaging, and tested for texture, color, pH, bricks, weight, and shelf life. Multi-flavor mixing is also supported. After curing, differently flavored gummy bears can be blended in programmable mixing drums. Servo-controlled gates release predetermined quantities of each variant, and slow tumbling ensures uniform distribution in every final package. Jolly Rancher hard candies are manufactured through a continuous high-temperature process that transforms raw materials into smooth, glossy, and intensely flavored glass-like confections. The production begins with the bulk handling of the base ingredients: granulated sugar, liquid glucose syrup, water, malic acid, flavor oils, colorants, and stabilizers. These ingredients are delivered in bulk: sugar in silo-fed dry transfer systems, glucose syrup in heated stainless steel tanks, and flavoring compounds in sealed drums. Each ingredient is stored under controlled conditions and introduced to the production line via automated PLC-controlled dosing systems. The process starts in the dissolving station. Granulated sugar is conveyed from silos through screw feeders into a large capacity dissolving vessel. Simultaneously, liquid glucose syrup is pumped from its storage tank into the same vessel. Water is added to reach the appropriate liquid content. High torque agitators mix the ingredients as the vessel heats, typically reaching 110 degrees Celsius. The sugar fully dissolves in the syrup, forming a thick, translucent solution. The resulting sugar-glucose solution is pumped into a high-efficiency vacuum cooker. This critical piece of equipment raises the temperature while lowering the pressure, allowing the mixture to be cooked to extremely high solids content without excessive caramelization. The syrup is boiled under vacuum to between 150 degrees Celsius and 160 degrees Celsius, reaching a final moisture content below 2%. The end product is a highly viscous, super concentrated candy mass nearing the hard crack stage on the sugar thermometer. Temperature and moisture levels are controlled by inline probes. As the candy mass reaches final cooking point, it exits the vacuum chamber under pressure and moves into a cooling and mixing table. This table is heated from below and cooled from above to bring the temperature of the mass down to approximately 120 degrees. Hot enough to remain pliable, but cool enough to allow incorporation of heat-sensitive ingredients. While the mass is still semi-fluid, malic acid, flavoring oils, and food-grade colorants are injected through precise metering pumps. These ingredients are introduced through static mixers built into the cooling table, ensuring even distribution. Each flavor variant, such as watermelon, green apple, cherry, blue raspberry, or grape, is handled in a dedicated mixing zone to prevent cross-contamination. The candy mass takes on its final color, aroma, and acidic intensity at this stage. After blending, the flavored candy mass is fed into a batch, former or continuous rope former. Inside this system, the mass is compressed and shaped into a thick rope using counter-rotating rollers. The rope is then pulled through a sizing system that gradually narrows and elongates it to a uniform diameter. Servo-controlled rollers and feedback sensors maintain consistent tension, ensuring that the candy rope holds steady dimensions along its length. As the rope advances, it enters a rotary forming die. This machine uses synchronized cavities on two rotating drums to cut and shape the candy rope into individual pieces. Each cavity matches the intended candy shape, a rectangular tablet with beveled edges in the case of Jolly Ranchers. As the rope is fed between the dies, individual pieces are sheared off and simultaneously molded into their final form. The forming process is extremely fast, with cycle rates exceeding several hundred pieces per minute per line. Formed candies fall directly onto a moving belt, which carries them through a cooling tunnel. The tunnel is divided into zones with gradually decreasing temperatures, typically from 25 degrees C to 10 degrees CC. Chilled, filtered air circulates above and below the conveyor. This controlled cooling ensures that the candy sets uniformly without developing sugar bloom, cracks, or warping. The candy surface hardens into a glossy, non-sticky shell with a glass-like texture. After cooling, the candies are conveyed to the wrapping station. A high-speed flow wrapper aligns the pieces single file using vibrating rails and timing screws. Each candy is fed onto a roll of waxed or metallized film printed with branding and product details. As the candy moves forward, the film is folded around it and sealed longitudinally with a heated crimping wheel. The ends are simultaneously twisted or heat sealed, depending on wrap format. Wrapping speeds often exceed 1,000 candies per minute per line. A vision system checks each wrapped candy for seal integrity, print registration, and size conformity. Cameras detect misaligned seals, unwrapped pieces, or malformed shapes. These are automatically removed from the belt using pneumatic ejectors. Approved candies continue downstream to the bulk collection point. Wrapped candies are collected and conveyed into multi-head weighers or piece-counting systems for final packaging. For bagged formats, vertical form-fill seal machines form pouches from roll stock film, fill them with the target weight or count of candies, and seal them with heated jaws. The top and bottom seals are crimped, and a tier notch or zipper may be added depending on format. Inkjet coders print date codes and batch numbers on each bag. For assorted packs, mixing drums or belt combiners randomize candies from multiple flavor lines. Servo-controlled gates release each flavor in programmed ratios. Blending is continuous, monitored by optical sensors that track color distribution across a moving belt. After primary packaging, bags are grouped into cartons. Carton erectors form boxes from flat blanks, apply glue or tape, and receive packs via robotic pick-and-place systems. The boxes are sealed, date-coded, and labeled with product information. Each box is checked for completeness using weight sensors or barcode scanning. Cartons move to the palletizing station. Robotic arms stack cartons in interlocking patterns onto wooden or plastic pallets. Slip sheets are inserted automatically between layers to improve load stability. Once the pallet is complete, it is transferred to a stretch wrapping station. A rotating arm applies stretch film tightly around the stack. A label printer applicator places barcoded shipping labels on two adjacent pallet faces. Each major system, dissolvers, vacuum cookers, batch formers, rope sizers, rotary molders, cooling tunnels, wrappers, weighers, and case packers, is governed by programmable logic controllers. The PLC network is linked to a central SCADA system, which visualizes process parameters in real time. Operators monitor syrup concentration, cooking temperature, rope speed, forming pressure, wrapping rate, and line efficiency from control stations positioned throughout the plant. Ingredient traceability is built into the software. Every raw material lot is scanned upon arrival, stored in the ERP system, and assigned to a batch number. As the batch flows through cooking, forming, and wrapping, each step is logged automatically. Final products are traceable by barcode to their raw material sources and production parameters. Clean in-place systems run automatically at the end of each shift. The dissolvers, pumps, piping, and mixing tables are flushed with hot alkaline solution, followed by clean water rinses and sanitizing cycles. Cooling belts are brushed and vacuumed. Forming dies are disassembled, cleaned manually with food-grade solvents, and reinstalled using quick clamp mechanisms. The entire factory is divided into controlled zones: raw handling, cooking, forming, packaging, and palletizing. Positive air pressure is maintained in high hygiene areas. HEPA filtration systems remove particulates from circulating air. Ambient humidity and temperature are tightly regulated, as both influence candy texture and crystallization. Factory floors are sloped for drainage and sealed with epoxy for easy sanitation. Safety systems include temperature interlocks, overpressure valves, infrared burn detectors, and emergency shutoffs across all cooking and forming zones. Machines are equipped with safety guards and light curtains. Wrapping and cutting stations include trap guards and automatic stops when foreign objects are detected. High-volume candy factories operate multiple parallel lines to meet demand. Each line runs continuously, producing tens of thousands of Jolly Ranchers per hour. Combined output can exceed 1 million pieces per shift. Candy that fails inspection or is generated during startup and shutdown is collected in a reclamation bin and disposed of or recycled in non-retail applications under controlled conditions. Jolly Rancher production is a fusion of sugar chemistry, thermal control, servo-driven precision, and automated material handling. The transformation from dry sugar to glossy hard candy involves phase change, concentration, superheating, and rapid cooling, all while maintaining tight tolerance in size, shape, and texture. The candy's signature clarity and smoothness are the result of precise cooking and air-free handling. The bite resistance and slow dissolve are dictated by gelatin-free formulation, extremely low moisture, and uniform crystal inhibition. Color intensity, tartness, and flavor intensity are tightly tuned in, dosing systems calibrated to deliver fractions of a gram with every cycle. No part of the process is manual. From sugar loading to pallet stacking, each action is governed by machines, motion controllers, thermal sensors, and inline verification tools. Each Jolly Rancher is cut, formed, cooled, wrapped, inspected, and packed in exact synchrony with the line's conveyor rhythm. The process is repeatable, uninterrupted, and engineered for scale. Nerds candy production begins with granulated sugar as the core ingredient. Delivered in bulk via silo trucks, the sugar is stored in food-grade silos and transferred into the system through pneumatic conveying lines. The sugar crystals are metered using loss-in-weight feeders and introduced into the initial tumbling drum, the nucleus of the entire Nerds production process. The defining characteristic of Nerds is their irregular pebble shape and crunchy shell. This is achieved through a continuous layering process that transforms small sugar crystals into larger, asymmetrical, coated pieces. Production starts with microcrystalline sugar particles selected for their uniform size and dryness. These seed crystals are placed into a slow-rotating stainless steel coating drum. Inside, the environment is warm and dry, with dehumidified air pumped in to prevent clumping. As the drum rotates, a fine mist of sugar syrup is sprayed onto the tumbling seeds. The syrup is composed of dissolved sugar and glucose, kept at a precisely controlled temperature and viscosity. After each syrup spray, dry granulated sugar is dusted onto the seeds. The wet syrup binds the dry sugar, and centrifugal motion within the pan ensures even distribution around each particle. The syrup sugar drying cycle is repeated hundreds of times in quick succession, forming rough, uneven lumps that define the Nerd's shape. Drying occurs continuously using a stream of low humidity, temperature-controlled air directed through perforated panels under the rotating pan. The airflow evaporates moisture from the syrup, setting each new layer of sugar into a hardened outer shell. The mass increases by milligrams with each cycle. The longer a particle stays in the pan, the larger and more jagged it becomes. This tumbling and layering process continues for 45 to 60 minutes per batch. Throughout the process, Real-time particle sizing is conducted using an inline imaging system. Cameras mounted above the pan capture live footage and analyze the average diameter and surface profile of the particles. Once the growing nerds reach target size, they are automatically discharged through a slide gate at the base of the pan. The rough white sugar lumps exit into a vibratory conveyor that removes dust and separates underdeveloped pieces. Air jets blow away fines, while a mesh sieve sorts by size. Any particles below the acceptable size threshold are recycled into the seed stream for the next batch. The acceptable pieces move toward the coloring and flavoring stage. Flavoring begins with batch division. The uncolored nerds are split into flavor groups: grape, strawberry, watermelon, cherry, lemonade, and others. Each group enters a dedicated coating pan where they are flavored and dyed. These pans operate at higher rotation speeds to encourage rapid coverage. A fine mist of ethanol-based flavoring and food-safe dye is sprayed onto the tumbling pieces. The formulation includes fruit acids for tartness, aroma oils for intensity, and synthetic or natural dyes for color. The sprayed flavor and color mixture penetrates the porous surface of the sugar nugget, resulting in bright, vibrant colors and intense taste. As the solvent evaporates, the flavor becomes locked into the outer layer. Color intensity is monitored by spectrophotometers mounted above each pan. If deviation is detected, the spray nozzles adjust dye concentration in real time to maintain consistency. Once flavored and colored, the nerds are dried and cooled using forced ambient air blown over vibrating conveyor beds. These conveyors are lined with food-safe mesh belts to allow airflow from below. The drying stage ensures that the candies are free from any surface moisture or tackiness. Target surface temperature falls to around 20 degrees to 25 degrees Celsius. The final coating step is polishing. Polished nerds exhibit a glossy, non-sticky exterior that resists clumping. Polishing pans, similar in structure to coating pans but lined with smooth, non-stick material, are used for this purpose. As the candy tumbles, a mixture of carnauba wax and food-grade glazing agents is sprayed in a fine mist. The pans rotate at medium speed, allowing the nerds to rub against each other and buff their outer surfaces. The process lasts around 10 to 15 minutes per batch. The polished candies pass through a second set of sifters and inspection belts. Optical sensors identify off-color pieces, misshapen forms, or oversized clusters. Air jets remove rejected items from the conveyor and send them to the waste stream. The remaining pieces are ready for blending and packaging. Nerds are sold in assortments, which means different flavors must be combined in accurate ratios. This is managed by a computerized batching and blending system. Each flavor is held in a vibratory feeder that releases product onto a shared conveyor belt in precise weight percentages. Real-time flow rate monitoring is conducted using load cells beneath each feeder. The combined stream of multiple flavors forms a randomized mix of colors and shapes that fills each package. Packaging is handled by vertical form-fill seal machines and custom filling stations depending on container type. For the iconic dual-chamber box, a specialized dispenser fills two parallel compartments simultaneously. Each compartment is connected to a dedicated flavor feeder, ensuring separated streams of two flavors into the same package. The box is folded from flat blanks using a rotary carton former, and hot melt glue is applied to the seams. A hinged paperboard flap is inserted as the opening mechanism. As the boxes move down the line, a laser coding system marks each with a production batch, date code, and serial trace number. A high-resolution vision system verifies the print quality and scans the surface for correct alignment and structural integrity. Any faulty boxes are removed by push-arm rejectors and sent to the quality hold station. For other formats, such as pouches, tubes, or novelty containers, Nerds are portioned by either piece count or net weight using multi-head weighers. These machines use radial feeding trays and weigh buckets to measure out small portions with extreme accuracy. The weighed product is released into packaging film or preformed containers, sealed and passed through metal detectors for safety compliance. Once packaged, the product is conveyed into case packers. Here, robotic arms pick up individual units and place them into corrugated shipping boxes according to a preset stacking pattern. Case sealers apply hot glue or tape to close the cartons, which are then labeled and conveyed to the palletizer. Automated palletizers use robotic gantries to stack cases onto wooden or plastic pallets. Each layer is placed with millimeter accuracy to maximize vertical and horizontal stability. Slip sheets are inserted as needed to prevent shifting during transit. Once the full pallet is stacked, it moves to a stretch wrapping station. A rotating arm applies tension plastic film to secure the load. A printed label with shipping information, SKU, pallet number, and barcode is applied before the pallet is routed to the warehouse. Throughout the production line, programmable logic controllers manage all operations, from syrup spray timing to coating pan rotation, flavor dosing, weight checking, and packaging synchronization. A centralized SCADA system displays real-time data on batch progress, line speed, environmental conditions, and machine health. Operators can adjust parameters through touchscreen HMIs without stopping the line. Clean-in-place systems are used for syrup lines, coating pans, and mixing tanks. At shift's end or during changeovers, hot water and cleaning detergent are circulated through the spray nozzles, pipes, and pump systems. Coating pans are wiped down, and flavoring stations are flushed with ethanol to remove residues. Inspection cameras and flavor-specific tools are verified between batches to prevent cross-contamination. Air quality is maintained by HEPA filtration, especially in the syrup spray and flavor coating zones. Airlocks separate high-precision areas from packaging zones. Temperature and humidity are maintained to within +1 degree Celsius and +3% RH throughout the production floor. All surfaces are made of stainless steel or food-grade polymer, sloped for drainage and sanitized daily. Ingredient traceability is enforced from raw sugar intake to finished package output. Each micro batch of flavoring and coloring is tagged with barcodes and scanned into the production system. Every box of Nerds can be traced back to its sugar batch, flavor addition time, pan number, and packaging line.